2018. And the objective is to develop the ceramics additive manufacturing applied on medical and aerospace field by covering the whole value chain from elaborating feedstock to testing product for commercialization. And also is to create a certification or qualification evaluation of the early stage researcher. This is a name for PhD for European project. And it's on ceramic additive manufacturing mainly. You can, if you can see my mouse, maybe I will put a laser pointer, kind of, yeah. You can see on the representation, the value chain here, and the innovation scale here. And we can see also a number of industrial and university. And we would like to create many product or process or characterization for the customer and end user. And for that, we will work with physics, chemistry, and mechanics. And this is the main domain of the ceramics 3D printing project. Now, if we can speak about the consortium, it's a very great consortium from my point of view, with 6 academics, main university and research center, 1 non-profit organization, and 7 industries. And it's spread everywhere in Europe, on 7 countries from UK, France, Belgium, Italy, Austria, Romania, and Turkey. And we have 7 countries, 14 USA, and the global budget is close to 3.5 million euros. Now, if we look the work package and the research objective, it's a matricial project. You have from one hand the value chain of the ceramics 3D printing, and from the other hand, the pillar to transversal work package. And you can see also the number of SR for each work package, which are here. And for the transversal work package, many times all the SR is involved in that. I will not try to do some optical test for reading because it's very small, but we can go to the other slide when I will be able to describe at least the research objective. The work package 1 is focused on material feedstock, and the research objective is to develop feedstock customized for 3D printing additive manufacturing at reduced cost. For the research objective 2, it's a process equipment. It's to design and build the next generation of 3D printer and strategic specifically dedicated to ceramic production. The work package 3 is focused on design and product. It's to correlate input data to output produced ceramics and demonstrate it for application. The work package 4, it's on testing and standard. It's to define and establish standardization, regulatory issue, and qualification and risk analysis. And the work package 5 is in modelization characterization. And the goal is to increase knowledge and modeling and characterization. The work package 5, it's also a scientific work package, but it's also a transversal work package because we need modeling and characterization for all of other work package. Now we can shift to the work package which are not a research one. The work package 6, it's a training networking. It's to form PhD and retrain collaboration in the multidisciplinary, international, and intersectoral environment. So package 7 is focused on management and dissemination. Is to manage project and disseminate knowledge and product to various communities. And the work package 8, it's an ethic requirement. It's to ensure compliance with the ethic requirement that the project must comply with. And this is all of the work package on this project. And each work package main leader will explain in detail what is included inside. I would like also to show you the picture of all of the ESR, which are here, and again, all of the people involved in this project. I can name it at least one time. There's the ENPT of Toulouse, which are the coordinator, the University of Birmingham, the Serum Company, the INFLPR, Air Maxon Company, the Marion Technology Company, Université Polytechnique Hauts-de-France, as a Lincotech, it's a company also. A Secua, it's a non-profit organization. Merced Boostech is a company. CRBC, it's academics. Optalm, it's a company. Gazi University, it's a university. And Litos, a company. And I think it's time to shift to the other part. But I would like to thank again all the people to be here for this public event on the DOC-3D printing. It's also the final event. Thank you for that.
So the first presentation will be the Work Package 1 leader. So that's Stefan.
Yes.
Can you share your screen?
Yes, please. So hi everyone. First of all, thank you also to Guillaume and David for to have this organization during the last 4 years now for this project. Of course, it was very, very interesting for us to participate to this project. And I am so Fabrice it's a shame that Fabrice will not be here today. He's very sorry about that, so he asked me to replace him. And so at the BCRC, we were the leader of the Work Package 1, dedicated to materials and feedstock. And of course, everyone knows about the importance of having a powder and or feedstock completely fits completely the needs of the ceramic processing. It's the case for every kind of ceramic processing, not only for 3D printing, but for 3D printing. Everybody knows that there is a lot of advantage with these technologies, but if you don't have the correct feedstock or correct powder, okay, the properties will not be very interesting at the end of the process. So in this work package, the main objective, as David said, is the development of, the development and supply of ceramic precursors suitable for the envisaged 3D printing technologies. And within this work package 1, 4 PhD were engaged. ESR2 and ESR3 projects were devoted to powder design with a review of existing 3D printing technologies and their related feedstocks. There is also a sub-objective of adaptation and characterization of ceramic powder for SLS or SLM systems, and also investigation of newly developed 3D printing process. And as far as ESR1 and 4 are concerned, they were devoted to suspension design with an adaptation and characterizations of ceramic slurries for stereolithography, adaptation and characterizations of ceramic slurry precursor from pastes or gels, characterizations and validation of feedstock formulation, and also reproducibility, shell life, optical absorption, debinding, and sintering abilities. So we were also so happy to collaborate with all these partners in the work package 1. So Marion Technology, University of Polytechnique of Hauts-de-France. So we were the leader here at the BCRC in Mons, Litos, so Toulouse, and also Serum. Of course, if you ask me for having what was the objective achieved or the results are there, of course. These 4 PhD that were passed within the last 2 years with Nicolas, with Giovanni, with Pedros Jesus, and with Chirong. And I think my role here is not to be to take some time, too much time. Sorry, I think that's the best will be to give the floor to the PhD for their presentation. So please, if maybe I don't know if I do the chairman for this session. If yes, I would like to propose to Nicolas to start his presentation.
Yes, perfect. Thank you. I think you could be the chairman. It could be very nice.
Yeah, please.
Yeah, and okay, just go. Maybe I will put you also permit co-host.
Yeah. Good morning, everyone. So I will share my presentation. Yep. Can you all see the presentation perfectly? Yeah. Okay.
Yes.
So it's a pleasure for me to be here today for this final event of the 3D printing. So this great project. So today I will talk about a brief summary of all my results for these past 3 years in the project. Actually, I defended like almost 1 year ago, a bit more than 1 year ago. And my topic was the development of substituted calcium phosphate for improved thermal stability processed by additive manufacturing, and more specifically the robocasting technology. So I was based, as you know, in the University Polytechnique de France at the Ceramat lab, and I did a great collaboration with the BCRC in Mons. So the main objective of my PhD was to improve the manufacturing of resorbable bone implants. Because these kind of implants are porous scaffolds, they can facilitate the adhesion and proliferation of the cells responsible of bone growing, osteoblasts. The porosity allowed the migration of cells and biological fluids, this porosity. So we wanted to use the benefits of additive manufacturing technologies to optimize the production of these bioceramic resorbable scaffolds, to have a controlled porosity, complex shapes, and to have like an on-demand fabrication for patients. So the material we studied in this project was the beta-3 calcium phosphate, beta-TCP. So it's a very well-known material for bone repair applications, since it has excellent properties as bioresorption, bioactivity, osteoconductivity. So it's already used on the market for bone filling applications. It can gradually be degraded in the body after implantation. So you can see here some forms of this product: granules, preforms, and pastes. However, there is still one issue with this material, especially for the densification, because it undergoes a phase transformation a bit more than 1100 degrees Celsius to alpha TCP. So it's the main material, but a different crystallographic phase. And this phase transformation occurs with a density decrease, lattice expansion, leading to micro cracks. So it's really a limit for the densification of this material, and so the mechanical properties of the implants. So we, in this project, we really wanted to avoid this alpha phase during the densification of the ceramic parts. In order to do that, we decided to use doping substitution way. So typically, by doping, we replace a small amount of calcium inside the lattice by other cations like magnesium, for example. And this doping allows the stabilization of the beta phase and to postpone the phase transformation at higher temperature, and also lead to other benefits like smaller grain size, improved mechanical properties, as also biological properties. So to realize the synthesis of doped beta-TCP powders, we decided to work with the wet chemical precipitation process. So the first step was to precipitate a calcium phosphate precursor by typically adding a phosphate solution into a calcium nitrate solution, and in this solution also add some dopants to include them in the lattice of the final beta-TCP. So after this precipitation step, we had a calcination step where the precursor was calcinated to completely convert this precursor to the final doped beta-TCP powder. So during these 3 years, we tested different doping rates with mainly 4 different dopants, cations: so magnesium, strontium, copper, and silver. So I won't go into too much details why we choose this, but typically mainly because they can increase the thermal stability, the mechanical properties, but also mainly for silver and copper. They can provide some antibacterial properties to the material. So we did also co-doping, so combining different of these dopants until the very nice composition with the combination of these 4 dopants at the same time. So of course, we performed a lot of characterization of these powders, so X-ray diffraction to analyze the phase at the end of the reaction, also infrared spectroscopy to analyze the purity, so complement to the XRD. Also, we calculate the real value refinement to get the lattice parameters to have a proof of the doping of the material. And finally, we had a collaboration with the Marion Technologies company for ICP-IS process to get like the atomic ratio of dopants. So we published in this paper in Open Ceramics about all these characterizations. So the first step, the next step after the synthesis, the calcination, was the milling to optimize all these powders to make them, as Stefan said, appropriate for the shaping process of ceramics. So first we studied a traditional shaping technique, the slip casting, to produce pellets and to study more deeply the sintering of these materials. So we compare 2 different kinds of sintering: conventional sintering and microwave sintering. Can be very fast and beneficial for the microstructures, with 3 different temperatures to assess the whole temperature of the phase transition of this material. So we compare these 2 techniques in terms of phase analysis, microstructures, mechanical properties. So as you can see here on the left, so the XRD of the different composition for conventional sintering at 1300 degrees Celsius, and on the right the same, but for the microwave sintering. And the interesting results here is that we have at this high temperature the absence of the alpha phase all the doped composition except for 1, which is less stable. So that's a very good result that means that we can sinter this material at higher temperature with the presence of dopants. We also observe like the grain size after sintering for both microwave and conventional sintering. And the main result here is like both the doping and the microwave sintering allows us to reduce the grain size of the sinter pellets after sintering. That can be very beneficial for the mechanical properties at the end. So this result is mainly visible for the undoped CP with the microwave, as you can see here on the top right, and also for the doping with magnesium, as we have like very dense microstructures with this doping. We also perform mechanical properties of these pellets, mainly Vickers hardness and elastic modulus. And we, as you can see here on the graph, we saw that the presence of dopant clearly increased the Vickers hardness and the elastic modulus of the sinter pellets compared to undoped CP, as you can see in red. So it's a very good results for the realization of bone implants. And also these mechanical properties were quite high compared to previous works on undoped CP made by, for example, isostatic hot pressing. So yeah, that was a very good result for us. We also had a collaboration with the Matisse lab in Lyon to perform biological analysis to assess mainly the cytotoxicity of this composition, because the presence of dopants, mainly silver and copper, can be toxic for the cells. So with this cell proliferation study, we were able to see after a few days. So here on the slide, you can see after 6 days, the proliferation of the cells on the surface of our pellets, undoped but also doped pellets. So the result means that the composition here is not cytotoxic, because the cell can proliferate and grow on the surface of these pellets. So that's promising for the use of this composition for bone implants in the body. And we submitted a paper of this on the Journal of the American Ceramic Society, and still waiting for review. Yeah. So after the shaping by traditional techniques, we study the additive manufacturing process with robocasting in the BCRC and the production of or inks with these powders. So the robocasting was a very good technique for us, since it's very reliable. You can use it with a wide range of materials, with typically low organic binder content, so it's easier for the binding. We are able to produce complex structures with this technique, and usually the mechanical properties are better compared to some powder-based additive manufacturing technologies. So for this step, we first prepare, optimize some inks. So typically mixing our beta-TCP powders, undoped, and also doped powders with some dispersing agents, viscosity binder, flocculant, and mixing all these components together to produce at the end, as you can see here, a viscoelastic paste, which is suitable for rheological characterization, but also for the printing process. So we perform different kind of rheological characterizations to assess the good behavior of the paste. So typically viscosity curve to assess if we have shear tanning behavior for the paste to be extruded. Also viscoelasticity curves to have sufficient yield stress to extrude the paste. And finally, some thixotropy tests to see if our paste has a fast viscosity recovery after the extrusion, to have like good parts that can sustain, keep the shape after printing. So after all this characterization, we were able to see that the paste was suitable and ready to be printed with our process. So typically we use at BCRC this Delta Wasp printer. So it's a clay printer from an Italian company, Wasp. And in this process, so a pneumatic piston is used as well as a conventional screw to extrude the paste, as you can see here on the video. And after optimization of the inks, we were able to produce different kind of designs for dense parts to porous design. We also optimize the drying process to avoid or actually limit the defects and the issues we can have after drying of the parts. So typically warping, so deformation like this, or the cracks. So our optimized drying process was called osmotic drying. So we used actually a polymer solution to immerse the part inside, and with the difference of osmotic pressure, the water from the scaffolds was leaving the scaffolds to go into the osmotic solution, and like this we were able to dry quite fast the ceramic parts and avoid the presence of defects. So by applying this process, so the printing process, then the osmotic drying for 12 hours, and then a sintering step, we were able to produce this kind of small scaffolds, so dense ones, and also porous ones. We were able to reach quite high relative densities for this material. And we saw also that the presence of dopants increased a bit the relative densities of the scaffolds. So it's very good results for the realization of implants. Here some SEM pictures of the surface of these parts. So we see very nice surface of the filaments, and we were also into the we check also the cross section of the filaments, and we can see still some cracks and pores present. But like we noticed that the use of dopants, doped powders at least, is able to limit the pores and the cracks present in the filaments. So it's a promising results for the use of these dopants. We also performed some mechanical properties at the BCRC on the scaffolds by compression tests. We were able to see quite high compressive strength for all this composition compared to some literature data that previous author did before with rubbercasting of undoped BTCP powders. And we observe also that the use of dopants, mainly this composition with magnesium and strontium, we had like a better compressive strength compared to undoped BTCP powders. So still, it's a promising for the use of dopants inside the beta TCP. So as to conclude my presentation, I would like to say that during these 3 years, we were able to successfully synthesize different kind of doped beta TCP powders with these 4 dopants, cations. We were able, the publication we published where Doc-3D printing was acknowledged. So we are still waiting for society. And here is the list of the different communications I made during these 3 years and the awards. Yeah. So thank you for your attention. Of course, I will be available for your questions.
Okay. Thank you, Nicolas. I think we can still clap in your hand for you.
Thank you.
And if someone has some question in the attendance, please, it's the time for it.
I have some question, but if someone want to ask,
please, David.
Just I think we have some shutdown of the record, and maybe it could be nice if you can show to again what is the valorization of your PhD.
Okay.
I think it's in slide 20, list of dissemination and publication.
Yes. Okay.
Yes.
So this is the list of the papers we publish in the frame of this project. So the first one was about like the influence of dopants or the thermal stability on the beta TCP powders. The second one was the paper of Chloe, where we collaborated for the both like the synthesis of the powders, and she made like a optimization of suspensions. The third one was about the optimization of the robocasting process with the inks, and the last one is the characterizations of mainly mechanical and biological properties of these dope powders. Yeah. And for the presentation and posters and oral communication, so here the list of some posters and oral presentations in these 2 years. Yes.
Okay, I still have question, in fact, but
okay. That's good.
What is the main challenge of your PhD, and how you fix it?
I think the main challenge was to make like the transition from the synthesis of the powders to the optimization of the ink for the robocasting process. So we had like I mean, I had to stop doing the more synthesis and try to optimize this robocasting process to be able to, at the end, try to manufacture this powder. So it was at the beginning, we had to get used to the collaboration between BCRC and Maubeuge, but there was like already great collaboration spirit before I arrived, so it was easy. But yeah, it was really like the transition between the synthesis and really the manufacturing of these powders was tough because it was kind of new. So, but we did it perfectly with the great collaboration of the two teams. So yeah.
Okay, thank you.
Maybe other question? I have one for you, Nicolas. It's
yes.
No. After your thesis, what's can you just tell me about your idea before and just after your thesis of what you want to do now? Is there any change in your mind about what you thought about your future 4 years ago and now?
Yeah, actually, it changed a bit. When I started the PhD, I had like in mind to join a company right after, or startup or something more, application turn. But now I really appreciated like the work in research, especially at university. So now I see myself more in the academic career if I can, because I know it's very tough to get some positions. So yeah, I would like to stay in academia maybe for a bit.
Okay.
I think I didn't learn enough, so I want to learn more. Yeah. I hope it will be good.
Okay. Okay. Thank you once again.
Thank you.
Maybe can you tell us also what are you doing now?
Yeah, so now so it's been almost 1 year. Next month will be 1 year since starting a postdoc in the US, Georgia Tech in Atlanta. So we started together with Alejandro this on a new project, also additive manufacturing of ceramics, but try new chemistries to go towards a single step process without the use of sintering in furnaces. So, yeah. So I think we are doing some great job. Now Aaron will join soon next month, so it will be nice again to collaborate with people from the project. Yeah.
Okay. You still have question, maybe you know. I have another question, but it's what result are you most proud of?
Well, I think it's like the realization of some 3D parts by robocasting. So it was really nice to see that you produce some powders by yourself and you are able to shape it also by yourself. And at the end, get like these nice little parts. But yeah, I think that's I think I kept one as a souvenir. So yeah, that was the most exciting part. Yeah.
And if you discuss with a new PhD student, if you have one nice advertisement to say to this new PhD student, what could be?
Maybe not to be afraid of not making good results directly. I think good work and patience always pay. So even if something doesn't work directly at the beginning, you need to continue, make some research in the literature, talk to supervisors, colleagues to try to solve these problems. So yeah, not to give up and have some courage and passion. Yeah, and also try to communicate your research. I think it's very important. It's always a motivation when you go to conferences and you can, talk about your research. Maybe you can find new motivation, new ideas. So I think I would say not to stay in the lab too much and also go outside and share your research. I think it's very important.
Thank you again for this nice feedback.
Thank you for this and the organization of this great project. I think it changed all our lives. So yeah, thank you.
It changed also my life and the life of many other people here, I think.
Okay. Okay, it's maybe we can switch to the next one, which is Giovanni, I think.
Giovanni is not able to join the meeting because he's working now.
Yes.
He's working in a French company. It's a permanent position, but he sent to us
this presentation.
A record presentation. Yeah.
Okay.
And the supervisor of Giovanni, it's me, David Grossin from ENPT, and Delphine Marie, and we are online and we will be able to.
My name is Giovanni Bruno. Good morning. Hello, everyone. My name is Giovanni Bruno. I am the ESR2 of the project DOC-3D-Printing. And this study was supervised by David Grossin from INP Toulouse and Delphine Maury from Marion Technologies. And this study is going to talk about tailoring ceramic powders for additive manufacturing from synthesis to the final part. So, as a reminder of the project objectives, let's start with some context. In this research, we used alumina and zirconia, and these powder, they have applications that require high complex shapes, and there is an interest from the industry to develop complex shapes using alumina and zirconia cheaper and faster and better. However, there are limited options of zirconia and alumina on the market today. There is a need of new specific feedstock for additive manufacturing where we can control morphology, flowability, particle size distribution. So this is the main motivation of this thesis. It comes from the need to develop tailored ceramic feedstock for additive manufacturing. And to summarize the thesis objectives in 4 points, they are: 1. To synthesize and to tailor zirconia and alumina powders to suit powder bed selective laser processing and digital light processing. 2. To search for connections between the powder characteristics, the behavior during additive manufacturing, and the properties of the final parts. To evaluate the feasibility of scaling up the process to industrial levels, so from lab level to industrial level. And 4, to propose tailored ceramic powder feedstock to the additive manufacturing market. Okay, so jumping to the most interesting results achieved for zirconia and powder bed selective laser processing. We were based in publications that used graphite to enhance the absorbance of zirconia, and we tried to use another component that was titanium carbide, and in the end we reached a higher relative density than the one we were based in the beginning. It's a very similar one, but we also enhanced the processing window, so we can produce dense parts with a larger combination of parameters. So in the graph we can see the whole combination of laser power and laser speed parameters that presented dense parts in comparison using titanium carbide in comparison with zirconia and graphite. And here there is a list of the most interesting results achieved for the study of zirconia in powder bed selective laser processing. 5 to 6 kilos of 8% yttrium stabilized zirconia was synthesized and tailored, proving the concept of scaling up the production. And the absorbance of the powder was enhanced from 4.5% to 57.4% using 0.25% of weight percent of titanium carbide. And the main influence of the parameters were identified to the size of the part, the hatch distance, and the laser strategy. And the higher relative density reached was 97%. And the processing window, as I said before, is 95% wider than the study that we compared with. And the main challenges identified during this study was the constant formation of cracks, micro cracks, due to the laser strategy and the heat exchange and the rapid reduction of temperature, and the density variation by changing the design of the parts, it's the size or clearly the shape. And here there are some more interesting results about the study of alumina in digital light processing that came from the need to create high complex demonstrators in a short time. So the initial requirements were to have an uniform debinding, to sinter below 1600 degrees, to have enough mechanical properties to be handled, to be visually dense and easy, and a process easy and fast. So the first proposition was to use sheet-shaped alumina that could be printed with slurries with 20% volume of powder in the slurry, and it had a really good dimensional stability after debinding. However, a low density after sintering. So we took the option of using sintering aid additives, starting with titanium oxide and manganese oxide, up to 4%. And after the tests, as you can see here in some pictures, the results were pretty conclusive. So the uniform debinding was achieved with alumina, the sintering temperature was lowered to 1425 degrees. They were mechanically strong to be handled. At naked eye, it was defectless, so it was the purpose of the initial requirements. And it could be printed, debinded, and sintered in 24 hours. So all the objectives were achieved, and the main challenges were the color was brown, as we can see in the last one in the right, due to the additives, mainly the manganese oxide, and the diffusion of the additives during sintering. So it contaminated wherever it touched. And in parallel to the studies with alumina and zirconia during the thesis period, I could develop different studies in many areas, and here are some examples. The first one is a confidential one, so it was the development of a new alumina-based powder that showed really good results, and the design of 3D printable mask, as it was during COVID, so for some time we put some effort in this small project. the design of 3D filters that could be reusable. So the DLP of double gyroid 3D filters as well, with our colleague ESR7 from Serum, Islam. The DLP bottom-up of natural kaolin, as well alumina hydroxyapatite, vitroceramics, and another confidential powder that was very complex because the absorbance of the powder with the UV light was very low. It was complicated, but we reached really good results on that one as well. And to conclude, here are the main objectives of the thesis. And zirconia and alumina were tailored to suit digital light processing and powder bed selective laser processing, reaching a good density for both, and we were able to tailor slurries for alumina and zirconia. We were able to identify connections between the powder characteristics, the behavior during additive manufacturing, and the properties of the final parts. So the binding and sintering processing parameters, the absorbance, flowability, we connected many important points. The scaling up of the tailoring process was studied and verified, and successfully verified in many cases. So all the tailoring steps and the combustion reaction, mainly the combustion reaction. And finally, there are now more tailored ceramic powder feedstock available for the additive manufacturing market. And finally, during the time of the thesis, I was able to publish one article and participate of 2 others. There were 3 awards won. So the best oral presentation, 1 best poster contest, and the best photo award. And we participated in 6 congresses, 4 poster presentations with 1 oral presentation, and 1 event as a volunteer and 1 event as organizing committee. Thank you, everyone. Thanks for all my colleagues and everyone that participated during this project with me. And if you have any question, don't hesitate.
Okay. So is there any comments from maybe David or Delphine about the thesis of Giovanni or other? Of course, please be free.
Yeah, I will not ask a question, but because we are very involved on that, but it was a very productive PhD with a lot of samples. I think it could be more than 600 samples or something like that, which are produced. And it was a little bit a nightmare to characterize all, and also, but this sample was used to optimize parameters, and we use also specific methodology to to determine what is the best parameters for printing. And yes, I think it's if we extend more, Giovanni will create more and more samples. It could be a start of nightmare for people, maybe.
Okay. Okay.
I don't know, Delphine, if you have some comment or.
Yes. Good morning.
Good morning.
So yes, he got very good results. He worked a lot, and for me it was a very nice period. I think he enjoyed so his thesis, and now I think he enjoyed also his new life. So it's nice to hear your voice, Giovanni, today for me.
Okay.
And maybe we can say Giovanni is working in a French company. I don't remember the name, but he's in Lyon. And unfortunately, he cannot be here because he needs to work this morning on that. But it's nice also to see PhD students which find position very quickly after the PhD.
Yes.
Okay. Thank you. So can we go further with the next presentation? And I think it's Pedros Jesus.
Yes.
Please.
Hello, everyone.
Hello.
Can you see my screen?
Yes.
Okay, well, thank you very much, Stefan, for the introduction. Well, I think you know me already, but I'm Pedro Navarrete. Currently, I'm research associate in the Instituto de Materiales here in Madrid, more specifically in the group of biomaterials and regenerative medicine. And today, I'm going to talk about the most interesting research findings obtained during my thesis, my 3 years thesis, which I defended more than 1 year ago. I tried to make the long story short, and so I put the link to the complete thesis defense if you are more curious about the results obtained. So here I didn't enter into too much detail. This thesis was developed in Toulouse, in Toulouse INP, in the laboratories LGC and Finimat, and was supervised by David, Christine Frances, and Mallory Torban. So I will start. Just as a reminder of the project objectives, the objective of the thesis were the tailoring and characterization.
Do you want
of
to put your screen in full screen? In
okay.
presenter mode? Yeah.
Second. It's okay now?
Yeah. Okay.
Okay. Well, the objectives were the tailoring and characterization of calcium phosphate powder. More specifically, we focus on hydroxyapatite. I think you are already familiar with this powder and the good properties that it has for bone regeneration. We studied the sintering efficiency, the behavior of the powder in different additive manufacturing technologies. These were the selective laser sintering, melting, which we prefer to call powder selective laser processing. Also, one technique inside of the stereolithography category of additive manufacturing technologies, which is the mask stereolithography or LCD printing. Then we also characterize the microstructural and mechanical properties of the printed parts, and we compare with the objective tissue or tissue in which these parts could be applied. Okay, we move to the most interesting results. First, we perform the synthesis of the hydroxyapatite powder, even if the process was already optimized before I arrived. I was in charge of the scale-up of the process to try to increase the amount of powder produced. We were able to obtain these particles that you can see in the SEM micrograph with irregular shape, and also we observed that it had poor powder flowability. We also confirmed the purity of the powder by XRD analysis, and it was stoichiometric hydroxyapatite. Then we perform a wet milling process to try to reduce the particle size and to produce ceramic slurries, which will be spray dried after to produce a spherical powder, improving the flowability, which is a requirement for the selective laser sintering melting process. Then this wet milling step, we perform in this kind of milling, wet milling equipment. We were able to increase the energy efficiency and decrease the processing time by adjusting the different parameters, the stirrer speed, grinding media size, and also the solid concentration. The use of a surfactant was also needed to decrease the final viscosity of the slurry to avoid any kind of trouble during this step and the following one, the spray drying. We observed that a low specific energy was required to perform this breakage of the agglomerates due to the weakness of the aggregates themselves. We were able to produce high concentrated slurries, more than 50% in mass, with a specific particle size distribution, which we were able to tailor, and also low viscosity was our objective. Also, we didn't detect any alteration of the composition. We just observed a small contamination of the slurry by the iron present in the chamber and the stirrer of the equipment, but it's something that could be easily solved by changing the material. We could use ceramic coated chamber or stirrer to avoid that, but it was not so high. Then the next step was the spray drying of these slurries to dry and to produce spherical particles, which show better flowability. It was required to optimize the feed rate, solid mass fraction, and the binder dosage to optimize the process. The powder produced was composed of microspheres, showing a good flowability. We performed different methods to evaluate it, and it was in the range of good flowability, good enough for the use in a 3D printer. We tailored the final particle size, the microspheres, and also the distribution, the span, which are the main properties affecting the flowability. No alteration of the powder was observed through infrared analysis, XRD, different techniques. Also, we were able to use a pilot spray dryer in collaboration with Marion Technologies to try to scale up the process. We obtained good results, similar to when we use a more mini plant scale spray dryer. Then we arrived to the powder selective laser processing, where we use this spray dried powder. We were able to find a process window which allow us to produce solid and stable parts with high porosity. And also we observed that there was a change on the ceramic, on the crystal phase from hydroxyapatite. It occurred a phase transition into tetracalcium phosphate to calcium phosphate, which was not expected, but we know that changing the laser parameters, that could be improved. Also, graphite was used as laser absorption additive to perform the printing. Then, as I said, the powder composition, also the laser parameters could be optimized to try to increase the proportion of hydroxyapatite in the final parts. Low mechanical properties were obtained for these parts, but we thought about the idea of once we have the parts printed, even if they have low mechanical properties, we could be able, through thermal treatment or polymer infiltration, to increase these mechanical parts to be able to use it in the different applications, in low-bearing implants, for example. So we were able to print chlorapatite, which is a chlor-substituted calcium phosphate powder. And in this case, since chlorapatite is more thermally stable, it didn't experiment with any phase transition. It was also a very interesting result. Then we moved to another additive manufacturing technology. It's the mask stereolithography. In this case, after the synthesis of the powder, it wasn't required the wet milling or neither the spray drying steps. In this case, we just use a planetary ball milling to produce a more slightly decrease of the particle size. So we were able to tailor the stability and the rheology of the resin that will be used for the printing. We use a commercial UV photocurable resin to prepare these slurries. Then once that we print the different scaffolds that we can see in the images, it was required to design a debinding sintering step in a furnace at high temperature to pyrolyze the polymeric part of the scaffolds, then having finally a complete ceramic parts, bioceramic parts. No phase alteration was observed in this case in the scaffolds. This scaffold showed good promising results in terms of porosity. We're able to control the internal porosity of the parts with a good resolution. Also, the compressive strength of these parts was good enough to use in some interesting application in the biomedical field. Samples show a slow degradation rate, which is common in well-crystallized hydroxyapatite. Then thinking on the application, it could be useful, for example, for guide bone regeneration, which is just as used as using structures to hold the internal part of the, for example, maxillofacial region for some kind of surgeries. And in this case, a slow degradation rate is required for the implants. As a general result, the feedstock material, the hydroxyapatite powders, were synthesized and prepared, tailoring the different properties, adapting the properties to the different additive manufacturing technologies. The sintering melting efficiency of the powder was evaluated in both technologies, and we were able to optimize it to produce the parts. And finally, we characterize the different properties of the scaffolds. Some of them show very promising results. Well, I didn't want to enter into much detail in terms of graphs and technical results, but if you want more details, you can find it in the different publications that we were able to produce. A total of 5 publications are already available. 4 of them as first author, 1 review in collaboration with other ESRs, and a 6th article in collaboration also with Asif, another PhD student, is in the process of being submitted. I had the opportunity to be member of the organizing committees for 3 different events focused on additive manufacturing of ceramics. Also, I had the opportunity to participate in a total of 12 different congresses, 8 of them internationals, showing posters and other presentations related with the thesis. And also, I got nominations, and I was finalist on different awards related with the thesis. One was from the French Chemical Engineering Society's thesis award, and also finalist in Maths and 180 seconds. So this one is my last slide. I would like to thank you all the people involved in the project, and thank you for the opportunity. And as a reminder, you have the link there if you are more interested in the complete thesis defense with more details. Thank you very much.
Okay, thank you, Pedro. Thank you very much for your presentation. Is there any question for Pedro? No. I have maybe one question for you, Pedro, about your the resulting parts after we have created by SLS. You say, okay, the time. How long does it take to make this part first?
We printed overnight. So maybe 9-10 hours, but we can print several
of course,
once.
And Okay, did you, of course, I think you, of course, you characterize it and you see it maybe by scanning electron microscope or other thing. Did you see some cracks due to thermal shocks maybe, or?
Yes, we observed a high porosity,
Yes,
internal
high
porosity. Once it was interconnected, the entire part, which could be good for the different application for the cell penetration, for example. And also we observed close porosity that we thought it was due to the CO2 release during the process. So
because of the graphite
of gases. Yeah.
Okay, but also some cracks. Maybe it's that was my question, to say. Of course, if there is porosities, there is no problem, because for the application you can infiltrate it after with the polymers. You told that, okay, no problem. But what would be not very interesting it's the presence of cracks due to thermal shock. And did you have observed
yes,
that?
Yes, in some of the parts we observed cracks, but yeah, I mean, it was we didn't have too much time to optimize more the parameters.
I know.
So it was just trying to close the process window to be able to print something, and we succeed, but it's true that it could be improved even more.
Yeah,
also,
okay.
Yeah. Right now there are some printers that have for example, are able to hit the built-in platform to avoid this thermal shock. Also, there are some printers with, instead of one laser, 4 lasers, using one to hit the region and to try to control that.
Yeah, of course.
Also improvement.
The question, not the same question, but in stereolithography process, for after you have to debind and to sinter your part, and what is the time then?
It was very long. It was conventional
thermal
sintering. Yeah, it was like 3 days of process.
3 days.
I know that there are more innovative process to perform this debind and sintering that are the microwave sintering, for example, to reduce this time.
Okay.
So, yeah, it's also a space to improve there.
Okay, thank you very much. Thank you very much.
Thank you, Stefan.
And also maybe the last one question is the same as I asked to Nicolas. What is your future now?
Right now, well, recently I got an Spanish grant for a postdoctoral fellowship of 2 years here in Spain. Also, I'm continuously applying for new projects, Marie Curie postdoctoral fellowship. So I'm still in academia, say, yeah, but I moved from ceramic materials to more polymer, but still in additive manufacturing, more, still focused on biomedical applications.
Okay. Thanks once again.
Thank you very much.
So last two.
I have one question for Pedro. Do you prefer a mask stereolithography or powder bed selective processing?
Well, it depends on the material. For ceramics, I think it's more optimized the mask stereolithography right now. Powder bed selective laser processing,
Okay. It was not just about what you prefer to print, more not linked to the material, but
it's much easier the mask stereolithography also. With the powder bed, with the powder everywhere, you need to wear the mask, everything. The mask stereolithography is more friendly technique, let's say.
Okay. And do you have any idea about the future of the ceramic printing? What could be the best printing process in the future? Do you have something in mind, or what could be the best thing?
Maybe selective laser sintering melting is still in the last position, one of the last. I think it's very complicated still. Still for metals, you need a lot of time to optimize depending the alloy and the different materials. So for ceramics, it's even more complex. So I think maybe yeah, stereolithography, we obtain very good results. Robocasting, there are other techniques more optimized for ceramics. Yeah.
Okay, it was a tricky question. Sorry about that, but
Okay. Thank you, Pedro. There is no more question. We can move to the last presentation of for this session, and it's Chirong.
Hello everyone, nice to meet you again. So I'm gonna present the main work of my PhD. The title is Ceramic Powder-Based Hybrid Bioenergetic System. So according to the background, which is displayed on the figure that we can see, for the conventional bioenergetic process, the powder was distributed in the powder tank and were introduced by the roller or doctor blade to the building tank layer by layer. The liquid binder will be deposited selectively on the printed arrow. After the whole process, the 3D object will be printed out. For the advantage of bioenergetic is that it is fastest existing AM technology, which is cost-efficient and flexible. The material choices is also broad, and product size for the bioenergetics also can be easily scaled up. But for the drawback, for the bioenergetic is low packing density and usage of coarse particles in order to ensure the flowability, which lead to the low center density and poor finish surface. So, how do we overcome the limitation? In my PhD work, we have three-stage works. For the stage 1, which is to modify the suitable powder properties and printing parameters in conventional bioenergetic process, and stage 2, which uses post-infiltration to enhance the density further, and stage 3, which is using the laser ablation to refine the roughness of the surface. According to the figure as shown here, so in stage 1, that we developed a comprehensive methodology for the preparation of suitable ceramic powders and optimization of printing parameters for customized machine. And stage 2, which we use the ceramic suspension under vacuum with the post-infiltration to enhance the density of porous part. And stage 3, which is after each layer printing, we use a laser to refine the contour of the printed area in order to enhance the roughness. So for the machine, which is a customized hybrid bioenergetic machine developed by BCRC and Optech. The key points of the machine, which has a changeable feedstock feeding system and the laser integrated inside, which is used to refine the contours we explained before. So for the result in the stage 1, we have obtained different powders as shown here, and which are raw powders and freeze-dried powder, which are cohesive and with large particle size distribution and also present lots of agglomerates. The spray drying process successfully produces spherical particles, and by sieving at 100 micrometer of the main spray dried powder, that we obtain two different powder with different particle size distribution. The second fraction of the powder from the spray drying process, we can see it's spherical, but also the particle size is quite narrow and small, which lead to the cohesive properties due to the increased intraparticle forces. According to the flowability, of course, all spray-dried powder are free-flowing and cohesive powder have poor flowability. The flowability, which is indicated according to the Carr ratio and Hausner ratio. We also characterize the powder bed properties. We can see from the laser image that spray-dried powder free-flowing, which lead to the homogeneous finished powder bed, and also which are expressed by the roughness profiling here. And according to the packing density, that free-flowing powder which lead to the higher packing density compared with cohesive powder. So that's lead us to use 3 spray-dried powder to do the further printing test, which are comparable good properties. Before the printing test, I want to introduce two concepts, which is binder saturation and layer thickness. For the binder saturation, which is the volume of the binder deposited on each layer, divide the volume of the pores inside of the selected area. The binder saturation is also related with the layer thickness value. There's different saturation level by under saturation, well saturation, and over saturation. In order to reach the well saturation, that we have done lots of printing tests according with different powder to optimize have the binder saturation level and the suitable layer thickness. We can see according to the different powder, we have different optimized parameters which are also related with the powder properties. After applying all these optimized parameters, that we can successfully print in the nice objects, such as for mechanic strength and benchmark and filter of different size. After the thermal analysis, we also define the sintering profile, which reaching the 1600 degree for 6 hours for alumina ceramic. For the mechanic strength, we can see when we're using the unstiff spray-dried powder, which are main fraction, and under this condition, which reaches the highest mechanic strength and the density, around 130.2 megapascal after 6 hours sintering, which is also in our expectation that according to the literature as showing here. Also for the finger in here, we can see that when we increase the binder saturation, no matter which kind of powder we use, that relative density and compressive strength also increased, and at certain level it reached the plateau value, which means it actually for different powder it has optimized value printing parameters to have the best quality of the final products. Was showing here that with different powder around 17% of the saturation level, which is good to have the good products. So bring to the conclusion, if we want to print something nicely and also successfully sintering, for the powder, firstly we need to modify the particle size distribution to have a suitable distribution and the morphology which are spherical to ensure the flowability which is necessary. And this also leads to the higher packing density. For the printing parameters, the layer thickness has also to be larger than the D90 and by the saturation around 17%, which is good for different powder. Applying all the parameters, we can have nice objects and also successfully sintering. Finally, we reach 64.2% of true density and highest mechanic strength is 130.2 megapascal. And for the shrinkage, which are 15% of linear and 40% volume. However, we can see from the macro-city image that the obtained products are still porous, so which lead to our second part of work, post-infiltration. We use ceramic suspension under vacuum to do the post-infiltration to enhance density. During the process, we also investigate the suspension properties according to the viscosity and stability, and also drying process to optimize it in order to avoid the cracks formation. According to the result, we can see that the density improvement was finally around 33%, which is a huge improvement. And according to the SEM image, that from the surface that the particles in the suspension was well infiltrated inside and centered together with the skeleton body. Also from microcity, we can see that actually the porosity was decreased very strongly, and also there's a distribution of the porosity, but we will, in this part, we will explain later. We also investigate the influence of different factors. For example, in here, with more infiltration rounds, of course, the final density will be increased. And after 3-time infiltration, that we can reach 88% of true density, which is very high. And from the cross-section image, we can see and that the particles was well infiltrated inside without any ingredients in the horizontal level. And also from the measurement of macroporimetry, that the pores were highly vanished. Besides, we also investigate other factors. For the powder size we use for printing, the skeleton body, it doesn't has influence on the infiltration effect, And of course, with higher solid loading, which result higher rich final density, we can see only after one round infiltration with 78% of solid loading reach the same level of final density as 3-round infiltration with 58% of solid loading, which is quite promising result. We can investigate further if we are interested. And for the infiltration duration with certain level, actually it has no influence on the final effect. According to the porosity distribution, we can see from macro setting here that actually it has gradients according to the direction of gravity. And for the horizontal level, it's negligible scattering. By analyzing the particles in the suspension, that we think the gravity dominates the direction during the process, and also drying and sintering, which lead to this kind of porosity distribution. And also that's why the horizontal level, which is more homogeneous and scattered. From the image in here, we also can see that no matter which direction, horizontal or the vertical, which both has shown these gradients. Also for the roughness, for the top side, that the roughness is still quite poor, which we can also see that the pores was not really completely infiltrating inside, but for the bottom part, which is much more completely infiltrated, and the roughness is also quite fine. Bring to the conclusion here, we successfully did the infiltration to densify the porous part, and the different influences of according to the parameters on infiltration quality were also well analyzed. The infiltration mechanism and pore distribution were dominated by the gravity, which has resulted in a gradually vertical distribution. From the imaging here, we can see finally after infiltration, we reach a comparable higher density in binder jetting porous part. Also, from the macro view, that actually the accuracy of the printing doesn't change, which is also one of our expectations. So the last part of work is hybridized laser machining. Our object is to increase the printing resolution, of course. Compared with traditional machining, laser machining has no contact, and thermal and optical properties dictate no magnetic strength exerted, which is also flexible. The laser we use is a pulsed laser, which has ultra-short processing duration, strongly reducing the heat-affected zone, and extremely high pulse energy generated. Here is the information of the fiber laser we used. The emission wavelength is approximately 1060 nanometer, and beam width is around 60 micrometer. We also investigate the absorbability of the powder, that with and without dopant. We can see that absorbability of the alumina on this laser was very poor, and with dopant it increased a lot. So what's the effect? Clearly, we can see after printing, we use the powder without dopant, it has no effect after laser treatment. But with dopant, the laser track is very precise and clear. So what's the mechanism inside? When we add in the dopant in the powder, it helps the absorption of the energy from the laser, and after the laser energy accumulation, the organic phase and dopants inside of the powder will become the vaporization, and the created recoil pressure will lead to the explosion and remove this part, which is actually not directly removing the alumina ceramic, because the threshold value of removing alumina ceramic with laser is 30 joule per square centimeter, but the highest level we reach with different parameter is 11.1, which also side proof our explanation. So in step 1, we want to characterize the ablation track dimension with different laser parameters. So how do we define this dimension? We certify the zero level and across the track, which is the width, and also the lowest point of the track to the zero level is the depth. And then we have obtained the different value according to the different laser parameters, respectively power, frequency, and scanning speed. Of course, with increase the power, that pulse energy density increase and resulted track dimension increase. with increase of scanning speed when the path repetition decrease and resulted track dimension decrease. But for the frequency, it's both effect, which has upside effect that pulse energy density decrease and pulse repetition increase. That's why the trend is unclear here. But however, we have found the optimized range and to do the step 2. In step 2, we print this cube, and of course each layer we do the laser ablation. And for the SEM image, we can see clearly compared with printed sample, the laser ablated surface was well treated, and we can see here from the cross surface that the particles were well cutted instead of directly sintering or melting or destroy the surface, which is satisfied in our expectation. Then we characterize the roughness of the surface we measured. That we can see after laser treatment, it was nicely improved the roughness, which is very fine by a factor of 3 compared with the original one. However, the computative effect between the path energy density and path repetition when we change the frequency still exists. This is our next step to do the further research on this part to make more clear about the effects. And also, meanwhile, we have used the right angle and the curvature radius to indicate the accuracy and sharpness which treated by the laser and compare with directly treated by the printing. From here we can see that compared with directly printed part, the angle of the two surfaces almost reaching the 90 degree no matter which kind of frequency we use, and also the deviations compared with printed part is different level, which is improved a lot, which is promising as well. And for the curvature radius, of course, the theoretical value is 0, and also with higher laser influence, the energy, the delicate geometry feature will be destroyed. That's why with the lower frequency in here, we can see the higher deviation. But overall, the average value was also improved a lot compared with the pure printed part, which is also we are happy about the result in here. Bring to the conclusion, we successfully did the hybridized printing laser machining process in situ. We increased the roughness by a factor of 3, and also, of course, the accuracy and sharpness. An addition with dopants in the ceramic powder is necessary to increase the absorbability of the powder. And influence of different laser parameters on the dimension of the laser track is also investigated. And we can see in here is a printed surface, and here is a laser treated surface, and also here is well cutted, which is for us is the premier excellent result. Bring to the final conclusion. So in stage 1, we build the relationship between the material parameter and the process parameter with the final properties of our printed parts. We obtain the methodology to develop the biojetting products according to the material and process. Also, for the post-infiltration in stage 2, we successfully enhance the density highly, and also kind of brings this kind of methodology and also give new idea about pore loss distribution. For the stage 3, which is completely new work, we have used laser ablation by the jetting to refine the finished surface, which is also in our expectation. Here are all the scientific communication and publication I have done, and I really want to thank all my supervisor, my friends, my colleague, and also my family. Without your support, we cannot reach in here, so really appreciate it. Finally, thanks for your attention, and I want to thank again all my excellent supervisor and all my excellent friends in DOC-3D printing project. Also thanks to David and Guillaume, give us a chance to be in this project, and it will be our unforgettable memories. Because of my work, I cannot present in Toulouse to meet you, but I hope there is a chance in future to meet you again. Thank you. See you.
Okay. So unfortunately, Chirong could not come today, but yeah. So
maybe we can just say that Chirong is now working for Saint-Gobain in France, I believe.
yes, in Cavaillon, but actually, I think he will be transferred then to China in a few months, or okay, I don't know the time schedule, but yeah, indeed, it's at Saint-Gobain at Cavaillon. Yeah. I think that okay, it's obvious that all the ESR have done a very good work, and so we were happy to follow them. So Fabrice told me that he was happy to follow this work package, and he hoped to get the opportunity to do it again, of course. Yeah. So.
Okay. Thank you again.
Please.
For this,
you hear me?
Yes.
Yes.
Wonderful. I don't know why I didn't say anything, only go out and come back. Yes, yes, I wanted only to say about Chirong, yes, but Stefan explained that. Yes, the work was very nice with him. I think that Fabrice said that Chirong came many times in his office to have explanation and so on. That was, yes, this Chirong had wanted to succeed, and he did what was necessary. The problem is that he had two opportunities in China. He chose Saint-Gobain. I think that was a good choice because as he was not allowed to go back to China because of COVID regulation in China, he's always in France. And Saint-Gobain, as there was a factory in France, donc they create a position only for him. By waiting, they can go to China. But for the moment, it seems that I don't know. I don't know the future. I hope that it will be possible for him to come back to China, but I suspect he would prefer to stay in Europe with all the events in China. But I don't know. I don't know. We have some chat discussion, and then okay, it's yes. That is the situation of Chirong. It's pity for him, of course.
Okay. Thank you, Anne.
And I believe that we will now shift to work package 2. So Gökhan from Gazi University will introduce the work package. And after that, we'll have a presentation from each of the ESR from this work package. Gökhan, if you want to share your presentation.
Yes. You might need to speak loudly.
Maybe you can you see my screen now? And you hear me well? Hello, everyone. Can you hear me well?
Yes.
Yes.
Yeah. Perfect. Gökhan Küçüktürk from Turkey, working in Department of Mechanical Engineering in Gazi University. Okay. Within the scope of the second work package in our project, our beneficiaries are Gazi University and Ermaksan from Turkey, Belgian Ceramic Research Center and Surham from Belgium. For each beneficiary, only one ESR is planned and employed in this work package. Chloe was working in Belgian Ceramic Research Center. Mohammed was working in Gazi University. They have completed their study there. And Islam Bokas is still working in Surham, and similarly, Asifur Rahman is working in Ermaksan. I will summarize the research objectives of this work package and individual project of each ESR in this presentation. Actually, it is better to divide these main objectives in two groups here for SLA optimization, stereolithography, and creating a novel powder bed fusion technique designed for ceramic. In both cases, the process conditions needs to be tailored, improved, and it shows that how important preheating, preparation of feedstock, which is processed, and post-treatment techniques, methods needs. For SLA optimization, we can say the most important point is to choose right wavelength and to prepare feedstock material which is processed. So it's aimed to determine the interaction between wavelength and material. In second part of this main objective, creating a novel powder bed fusion technique process designed for ceramics. As we know, the absorptivity of any ceramic material is very low when a fiber laser is used for a device which is used for metallic additive manufacturing. Then to control some important parameter must be improving the material type must be improved and must be important. Therefore, Ermaksan is working on the new chamber design to control the important parameter, and Gazi University working on the optimum parameters to produce high accuracy ceramic parts for this aim. Summarily, we can say our beneficiaries' responsibilities are here. The optimization of process parameter for this SLM or SLS technique from Gazi University. The CRC plans to decrease the time in manufacturing and mainly focusing on the post-process design, and Ermaksan plans the innovative design for SLS and SLM for ceramic materials. For each ESR studies presented here for ESR 5 Chloe study, we can say mainly focusing on the manufacturing of bioceramic complex structure using stereolithography technique to elaborate the porous structure using this technique and to reduce the sintering time and to obtain very fine microstructure. After these main objectives, she obtained good results. She tested different monomers to obtain resin suspension, and printing parameters were adapted to avoid, prevent some defects. After these all, she was able to produce some parts with high dense reaching over 98% with a wall thickness of 5 millimeters. For Mohammed's study, we can say mainly focusing on the investigation of pattern definition and sintering speed for these 3D ceramic printers, especially scanning strategies and scanning speed. After these, you see the objectives. Mohammed developed a new numerical model to determine the optimum process parameters to issue high quality printed parts, and this study shows that the aluminum oxide and silicon carbide ceramic materials can be produced directly with these techniques with a high quality and complexity, as you see in these figures, alumina and silicon carbide materials. When we check the Islam Bokas study, it's mainly focusing on the design, research, and post-process optimization of calcium phosphate-based 3D ceramic implants to make a design, new calcium phosphate implants and scaffolds with controlled parameters and investigating effect of design on the process. He's still going on the study, PhD study. Probably he will give more information about after my presentation. And the last ESR is Asifur Rahman, focusing on the effect of chamber dimension and laser parameter on the ceramic 3D printing. After these main goals, design of CAD model of sintering chamber, mathematical model of heat distribution, temperature distribution simulation, controller design for temperature control, and we expect that he will design a new apparatus and prototype production for a ceramic 3D printer. You see prominent published paper taken from Funding and Tental Portal's webpage. Of course, I know they have more than the published papers, just taking the prominent papers you see here in this. And two of them, ESR 5 and ESR 6, graduated, and two rest of them, our ESR, Islam and Asif, are still going on their studies. Thank you very much for your attention. Now we are starting with first ESR 5 presentation, if she is ready.
So my name is Chloé Goutani, and I was the ESR 5 of the DOC-3D printing project. And in this presentation, I'm going to briefly describe part of my work that was done during the PhD on the additive manufacturing of bioceramics, and more specifically on the optimization of the stereolithography process. Next. So in order to remind a bit the objective of the project, which kind of changed since it was defined. But basically, the first idea was to create a link between the orthopedics field, where there is a lot of need for bone implants due to disease or accident that can damage the human body, or osteoporosis, for example, that causes millions of fractures each year, and the additive manufacturing, which are technologies that enable to have a fast prototyping, the production of objects with complex shape, and provides a great adaptability. So combining that together, we got the additive manufacturing of bioceramic material, and by choosing the beta-TCP, so beta-3 calcium phosphate powder, which has a chemical structure very close to bones, the idea was to produce biocompatible and biodegradable implants adapted to each patient. Next. So more practically, what was the project about? Well, it was about developing a suitable suspension to be printed with powder produced in the LMCPA, also in the frame of another ESR project, and all of that with the ADMAFLEX machine. So the ADMAFLEX machine is the machine that was at the center, let's say, of the PhD, and that was provided by a company called Admatec, and is a DLP technology. So the UV light is flashed with a projector and works with a tape casting technology. And the suspension that was the basis of the printing was made of a photosensitive resin composed of different monomers and a photoinitiator and some bioceramic powder. And this was the material to be developed and optimized. Next. So it was decided to work on 3 different axes. So first, the powder that had to be coated with a dispersant in order to be suitable to be printed, and from which we developed the sintering cycle. And this powder was chosen, as I explained before, specifically for the application in the biomedical field. Next. Then we worked on the resin as well. And the resin composition was completely to be defined, again, in order to be suitable, to obtain a green part with as few defects as possible, and then to develop the debinding cycle. Next. And finally, some work was done on the machine because the process parameters had to be adapted on our customized, let's say, suspension in order to obtain a dense ceramic part. Next. So regarding now the most interesting results achieved, well, it was possible to coat the powder that was provided by the LMCPA, as I said before, with phosphoric ester as a dispersant and a 3D rotational mixture that provided both steric and electrostatic repulsion and enabled, therefore, to obtain a stable suspension and avoid quick sedimentation. Next. So then the manufacturers of an homogeneous suspension was possible. So the powder and the resin were combined together using a speed mixer machine that uses a dual centrifugation force and enabled to very quickly obtain a suitable suspension to be printed. Next. So the resin composition was investigated. Several monomers were tried in different concentration, and it was possible to achieve different composition that provided the lowest viscosity and that were viscosity that were suitable to be printed in the ADMAFlex machine. Next. Then the process parameters were investigated and different light power and exposure time were trialed in order to obtain the best printing precision. So a square shaped with squared hole was chosen in order for it to be easy to measure the dimension and to spot the overcuring that we absolutely wanted to avoid, and also to check the definitions of the angle that would give us good information on the precision. So finally, it was possible with a certain set of parameters to obtain pieces that were almost exactly like the original design. Next. Then the slice thickness was also investigated in order to avoid having surface defects that could create problems in the application. So with the optimum composition and the optimum light parameter, 3 different slice thickness were tested, 20 micrometer, 30 and 40. And it appears that with 30 and 40, less surface defects were present, and this provided parts with very good final quality. Next. So in conclusion, it was possible to manufacture a suspension that was printable with 2 different resin composition, and that was loaded with 48% volume of beta TCP powder. It enabled the printing of dense parts with a few defects. And when I mean dense part, I mean densities above 98% for parts that had a wall thickness around 5 millimeters. The light power and exposure time were also tailored in order to obtain the best resolution and to print parts that were exactly like the initial designs. Next. Then some complex shape were also printed with the machine with porosity gradient. And this kind of shape is particularly interesting in the biomedical field, as we know our bonds have not an homogeneous porosity. So it was interesting to know that this technology enables to print this kind of shape. Next. Then some first biological tests were done because it was at the end the ultimate goal to be able to use this species in the human body. And so this biological test confirmed the non-cytotoxicity of the printed part and also confirmed the bioactivity of the beta TCP parts compared to alumina parts that are bioinert. Next. And finally, as a proof of concept, we also try to investigate different debinding and sintering systems in order to speed up the process, and more specifically, the use of microwave debinding, where it was possible to debind in 90 minutes compared to 23 hours. However, this technology was not fully investigated in the frame of this PhD, but just gave a basis where we see that it was possible to debind with this kind of process. So thank you for your attention. And in the next slide, there will be the list of the different, so you can go on to the next slide where there is the list of the different disseminations. So an article was published during this PhD, and I participated to different conferences, basically in Europe, and won different awards as well. Yeah, so this was also a great experience that were done during this PhD. Thanks again.
Thank you very much for your presentation, Chloe. We can have question for Chloe's study, if you have.
May I have one question?
Yes, please, David.
My question, thank you, Chloe, for this nice presentation. My question is, what is the difficulty if you want to change from beta TCP, for example, to another materials with your process? Is it easy to change from one powder to another powder? Or?
Well, actually, this was also one of the goal of having non-made resin, is that we could use it with different kind of powder that were produced in-house, because sometimes with commercial suspension you can only have one kind of powder. So I would say it can be done, but it also depends on the absorption of the light that's that your powder does. But between, for example, beta TCP and hydroxyapatite, it has been done quite easily to change from one powder to another.
Okay, and do you have in mind how much time you need to do this change from one powder to another? If it's
I would say that now we have a basis on what kind of monomers that we want to use, and then you can still tailor the quantities a little bit to change the viscosity of your suspension. That could be fitted also depending of the grain size of your powder, but I don't know exactly how much time it would take. It would depend of the complexity of the powder that we want to use.
Yeah.
If it's just one simple granulometry, several zirconia, it's a bit different as well.
And I have one last question. It's if you dream about your printer, I know maybe it's not a good thing to dream about printer, but if you dream about
you know,
printer,
when you work 3 years on it, you start
and,
dreaming about it.
What kind of improvement you want to have in your dreaming printer?
Well, I think at the moment one thing that was restricted was the size of the pieces that we could print. So maybe having bigger building platforms could could like be something that would be very useful, I guess, to produce some difficult parts.
Okay, thank you. Is there any question for Chloe's presentation?
Maybe just we forgot to ask what are you doing now?
Yeah, what are you doing now?
So I'm working in a company called Vesuvius, and I actually did a very harsh change of field because I'm now working with refractory ceramics. But I still have some projects that involve 3D printing.
Okay, but you are still in ceramics at least.
I'm still in ceramics. Yes, that's
yes, for ceramic power.
Okay. Is there another question? Do we have? I think no. Then we can start with the second ESR, Mohammed. Mohammed, if you are ready, you can get. Thank you. Thank you.
Yes, can I share my screen? Okay. Okay.
Do you want to share? Oh, okay.
Yeah.
Okay.
Yes, we can see your screen.
Yes.
Okay. Hello, everyone.
Hello.
It's my pleasure to see you again at the final meeting of DOC-3D-Printing. So my name is Mohammed Abdelmoula, and I was working in powder-based selective laser and melting sintering of high-technical ceramic material under supervision of Professor Curie at Gaz University. So first, I will start with a reminder of the project objective. First, we started with reviewing the past research in ceramic BBSLB. And we found that there is a real need to investigate this technique in depth, especially the process parameter, which are laser power, scanning speed, hatching space, and scanning strategy, and layer thickness and build orientation. The problem with these parameters that are they are dependent parameters. So if we change one parameter, we have to consider changing the other parameter. So also the direct powder-based selective laser processing of ceramic is a quite like difficult and challenging process, and there are many factors that should be considered for achieving this process. So first, we think about developing numerical models that can help us during the experimental work. So for the research objective, first we first to develop numerical models that can be used as a guide during the experimental work. Second is to investigate the effect of the process parameter on BB-SLB of ceramic, and then optimizing the process parameter to reach the optimal combination of this parameter, and finally mechanical performance evaluation of ceramic material. We decide to work into ceramic material, aluminum oxide and silicon carbide. For alumina, we first started with powder, because the raw powder we have in PCRC that is not like suitable for this technique. So we used spirit dry technique to modify the powder and also to increase the absorptivity of alumina powder. And finally, we have this is the final powder we used during the work. During the work, we have like flowable powder, as you can see here. After that, we validated the numerical model. We printed some alumina sample, and also we did some measurement to validate the numerical model to be used during the experimental work. Then we started with scanning strategy investigation. We investigated different scanning strategies, as you can see here, linear 0, 90, 45, and also different shape. And we found that linear 45 gave a promising result for aluminum. Then we use the numerical model to get the appropriate process parameter at different scanning speed, like 300 millimeter per second and 400 millimeter per second. And also we succeeded to print alumina sample using the parameter we obtained from the model, as you can see. For scanning speed, we found that using high scanning speed, we can get like high relative density, like more than 85%. And the reason for that using high scanning speed, the laser dragging force attract all the particles surrounding the scanning area. And this not happen with 100 millimeters per second, as you can see here from the building plate. Also, we did like some analysis for different scanning speed, and we found that using high scanning speed for alumina give us like better microstructure comparing to the other scanning speed. After that, we optimize the process parameter. We consider laser power and hatching space for optimization, and we used to gauge optimization technique to optimize the parameter, and we printed the treatment we obtained from the optimization technique, and you can see the sample were printed successfully. We consider the relative density and also the surface roughness as a response factor for guiding the optimization. And we found that to achieve like maximum relative density, we have to use a small hatching space, and also we have to use like intermediate laser power. And for surface roughness, we found that in order to increase the surface roughness of the sample, we have to reduce the laser power, and also we have to reduce the hatching space. Also, we use Berto-Anufa optimization technique to see the effect of each parameter. We found that for relative density, the most dominant parameter is the hatching space, so that we try to investigate different hatching space. As you can see here, we reduce the hatching space like 40 and 30, and we found that when we reduce the hatching space, we could obtain high relative density, like more than 94.5% using this hatching space. Also, after optimization, we check the microstructure. We could found that using small hatching space, we obtained a good microstructure comparing to the 40 micron and 50 micron hatching space. And this is like, we can see the final result. There is like a great modification in the microstructure. This is the microstructure before optimization, and this after optimization, there is a great enhancement in the microstructure, as you can see here. Also, using the optimized parameter, we could print some complex shape lattice structure. And also, we investigated the mechanical performance using compression test. We printed alumina sample using the optimized parameter, and we could obtain a compressive stress of about like 140 megapascal, which is like considered like a little bit comparing to the data. The value obtained in literature is about 3,000. This is mainly due to we have like cyclic damage along the build direction. So for the conclusion for alumina, so the first conclusion is that the development model is effective to predict the process parameter, and also the development model is effective also to interrupt the experimental result. And the optimized parameter we obtained for alumina is like scanning strategy linear 45 degrees, scanning speed 400 millimeter per second, hatching speed 30 micron, and laser power 210 watt. Also, using the optimized process parameter, we could obtain a readiness of about like more than 94%, and also we could print complex shape. For future, the first thing that should be considered like improvement in feedstock, because as you can see here that the powders that we use, we have like a porous structure in the powder, and this is mainly the cause for like the low surface roughness we obtain in the sample. So the first focus should be directed to the feedstock improvement, and also to reduce the layer thickness and using compaction for the powder, and also applying preheating and temperature control to prevent cracks, and also to reduce the residual stress accumulated in the part. For silicon carbide, we almost follow the same technique, same procedure that we use in alumina. First, we use the numerical model to obtain the process parameter. We investigate different layer thickness at different scanning speed, and also we obtain the laser power at each set. And as you can see here, and after that we investigated the scanning strategy. We studied for scanning strategy, and we found that increasing the strategy gave a promising result for silicon carbide. After that, we printed the silicon carbide sample at different layer thickness at different scanning speed. And also we found that using low scanning speed, we could obtain a good sample comparing to the high scanning speed, 250 and 500 milliliter per second. We have some problems here along the build direction. You can see there is some delamination and also some defect in the top surface of the samples. Also, at 30 micron layer thickness, we had almost the same conclusion. We have a good sample at 100 milliliter per second, but for high scanning speed, we have still some defect in the samples. For 40 micron layer thickness, in all scanning speed, we have like defects, and we have like some delamination along the building direction, and also we have some interlayer, as you can see here. So we can see that 40 micron is not suitable for silicon carbide. Also, we investigated the compaction effect. We studied different compaction ratio like 100, 200, 300, and we found that increasing the compaction lead to increase the relative density, as you can see here. After that, we optimized the parameter. We used laser power, centering speed, and hatching space as a parameter we consider during optimization, and we used to gauge optimization to get the treatment for each process. And we printed silicon carbide using this treatment, and we could directly print silicon carbide in metallic base plate, as you can see here. For the result from optimization, we can see that to achieve the maximum relative density, we have to increase the power, and we have to reduce the scanning speed, and we also have to increase the hatching space. For achieving maximum silicon carbide content, we have to use intermediate laser power, and we have to increase the scanning speed, and also we have to reduce the hatching space. For Bertinoff analysis, for relative density, the result gives us that the scanning speed is the most dominant parameter for achieving high relative density, and for silicon carbide content, scanning speed also is the most dominant parameter. So we couldn't try to reduce the scanning speed because we used almost the lowest scanning speed, 100 meters per second, so we couldn't change the scanning speed. So we tried to have a look for the second parameter, hatching space. So we printed some silicon carbide sample at different hatching space, as you can see here. And we found that, like, for example, for E6, if we made E6, that increasing the hatching space lead to increase the relative density. But for E7, increasing the hatching space reduces the relative density. Also, using the optimized parameter, we could print some complex shape of silicon carbide, as you can see here, and also we printed a cylindrical sample direct on metallic base plate. Also, for mechanical performance evaluation, we also use the compression test to evaluate the mechanical performance. We printed silicon carbide compression sample, as you can see here, and we tested this sample. We could obtain a compressive stress about 1.85 megapascal. This is very, very low compared to the value reported in the literature. It's about 3,900 megapascal. This is mainly due to that we need like to make post-processing to increase the densification of silicon carbide. So for conclusion, for silicon carbides, first conclusion that the model that we developed is was able to predict the percent parameter, appropriate percent parameter for silicon carbide, and also the developed model is effective in interpreting the experimental result, and the optimized parameter are for scanning strategy inclined zigzag, for scanning speed 300, for hatching base 45 micron. Convection 300, and this is about as calculated from some model. Using this optimized parameter, we could print silicon carbide sample with relative density like more than 84%, and also we could obtain print silicon carbide directly on metallic base plate, and also we could print complex structure of silicon carbide. So for future respect, we have. First, we should first to have like some focus on improvement in the feedstock, like have feedstock with the spherical powder, and also we should focus on preheating, applying preheating and temperature control to reduce the residual stress and cracks inside the samples, and also post processing to increase the densification. So for publication, I published about 5 papers, and also I placed my work in different conference, international conference, and there are about 3 papers we are going to submit maybe this month or next month. Finally, I need to thank everyone who supported me during my work. I need to thank my supervisor, Jochen Gutschler, for his help, for his support, and also I need to thank David and Joyam for their support during my stay at Toulouse, and also Fabrics and Enrique for their help at BCRC, and also my colleague at DOC-3D-Printing, and everyone. Thank you very much.
Thank you very much indeed, Mohammed, for your presentation.
Okay. Thank you.
We can have some questions if we have.
I do have one question, if it's possible, actually.
Yes, please, Eren. Hello.
Thank you. Hello. Thank you for
Hello,
the presentation. It's actually more of a curiosity than a question. Sorry, I'm a bit sick. Pardon my voice. I can understand it for silicon carbide pieces, but why your alumina pieces turn to black after process? Have you ever questioned this?
Yes, actually the printer at BCRC, it is like quite old. So it is about more than 10 years now. So the vacuum, they cannot vacuum like totally like 800. So they just vacuum it like 5,000. So this is mainly we have like high content of oxygen inside the chamber. So this is mainly the reason for the black color. And also because we try to modify the alumina powder, as you can see here, we have this is like a raw powder. We try to increase absorptivity, so we added some carbon inside the powder. So we have carbon content inside the powder, and we have like a high oxygen content inside the chamber. So this is the mainly reason for the black color of alumina.
Yeah, but you think that's caused any chemical change in your material, in your final product?
No. We checked. We make XRD, and also we did some characterization. We couldn't find any new faces, just aluminum. Yeah.
And have you ever tried to like cut your pieces into half and try to see what's in the core, like if you have the same structure everywhere around the pieces?
Yes, actually, I cut many samples and I present in my thesis. I think it is maybe in YouTube. Yes, I cut many sample, and also I did like some microporosity, and yes, it is available. Yes, I think.
Yeah,
YouTube, yeah.
Because I mean, your results are amazing. This island concentric out-in strategy, we like three of us, Alejandro. Yeah, this the one in the middle. Like Pedro, me, and Giovanni and Alejandro, everybody tried these parameters, and I think that didn't work out for anyone. And your results seem very, very precise and very nice. Like, congratulations for this.
No, thank you. Actually, this actually because you know the scanning strategy in BCRC is like concentric like out in. So there is like heat accumulation at the island, you know, at center of the island. So we have like a small hole inside the sample. We checked the samples. First, we broke the sample and we found that we have channels inside the samples. And also this channel like very wide at the top, and it is like almost closed at the base. This is mainly due to the heat accumulation, because you know when you print like many layers, we have heat accumulation. So heat accumulation makes the hole wider. So we did some characterization for this sample, yes.
But actually, this is very hard to obtain, the interior grid. So it's very good. Congratulations, really.
Yeah, thank you very much.
Thank you for your answers.
Thank you.
Thank you, Eren and Mohammed. And most probably David is going to ask.
Yes, I have one question to Mohammed. One question about the experimental part. It's for the black alumina, did you use some enhancement of the absorption using some graphite, or did you do some other treatment? I don't know if it's confidential or not, but just you can
give. No, we used just graphite. Yes, we added some graphite during like style formation. We added some graphite. After that, we spray dry the powder. Yes.
Okay. Yeah. I have another question which are linked to the simulation and modelization. And what is the main challenge for the modelization and simulation?
The first thing is the model is because there are many models in simulation. For example, there is micro models, there is macros, there is nano. So the first thing you have to decide which models that you need according to your work. So this is the first thing. After that, you have to you know, including all the equations. There is like an equation for heat transfer, for material properties, and for the laser heat equation. So you have to write all these equations in one file. And also you have to, we can see that interrupt this code to the program. It is like very difficult process, and it take many time for me. And the second thing is discretization, like the meshing. You have to select the appropriate mesh for your model. After that, you have to validate the model with experimental, because without validation you cannot make sure that the model gives us accurate result. So the most important after having the model is validation of the model, and it is like very difficult like process.
Okay, and what about the difficulty to obtain the initial information about powders and other printing parameter? Is it easy to find for you?
You mean for the model or what?
Yes, for the modeling.
Yes, first, for powder, I use like for example for alumina, I use the powder from BCRC. I take the properties from BS. They send me the properties like density equation, like this specific heat, and also I did some measurement for absorptivity and also for density. And for process parameter, I have to go to inside the software of the printer, and I have to get all the software like parameter limits from the printer, because simulation is we can see that you simulate the printer inside the computer, so you will have to all the information about the printer to take it as a code inside the software. So it is something like this, yeah. For example, in Toulouse, I contacted with Alejandro, and he sent me all the data about the printer, scanning storage available, the limit for power, for scanning speed. So I try to like make like virtual printer inside the computer. So this is like the main difficulties in simulation is. But actually, simulation helped me like a lot, because without simulation, really I couldn't do a lot of work. For example, for when we worked with silicon carbide. Without simulation, we could not print some carbide. We could not get like good samples. And also for alumina, the same, yes. So it has really helped me a lot. I reduces the experimental work, reduces the effort. I don't have to like print different sample with a lot of parameter. I just print the parameter that the model recommended to me. So it is really very helpful, yes.
Okay, thank you, Mohamed, for this nice answer. And I think it's allowed to explain to the other people how it's difficult sometimes or easy. The printing. I have one other question. It's links. Maybe could you just explain where you are now? What is your job?
Yes, now I am in Egypt now, but by the end of next month, I have a position in United States in University of Wisconsin, Milwaukee, as a research associate working on additive manufacturing of metal. So by the end of next month, I will join this university. Yes. Okay. But now I'm on holiday in Egypt. Yes.
Okay. And what is your expectation for the future?
Yes, actually, the project DOC-3D project helped me like greatly to shape my future. Without this opportunity, I cannot like have like this position. So it is really very helpful, this project for me. And my expectation, because okay, I started additive manufacturing, and also I will continue in additive manufacturing. So I think my expectation that maybe by like few years I will be like a good researcher in additive manufacturing. Yes, I hope.
But maybe you are ready, no?
Maybe.
Yes.
So. Yes.
Thank you. Do you have more questions? Or Mohammed? I think there is no question. I have a question. May I? Mohammed?
Yes, of course. Yes.
What is your idea for future of ceramic part produced by this technique? Is it possible to produce these ceramic parts with a high, sufficient mechanical strength? Is it possible for future?
I think yes. Powder-based electric processing is like a promising technique for ceramic, because, for example, for other technique, we need to make like slurry preparation, like need to mix the powder with other binder, and after that you have to print, and after that you have to make the binding and the centering. So there are like a long chain of process using other technique, but SLM or SLS, you directly upload the powder to the printer and then run the printer, and you get your part. But there is some point we have to consider, for example, because of the high melting point or high centering point of ceramic, and there is a ceramic choke happen inside the process. Maybe in the future, if anyone could like design a printer like for that have like some preheating to reduce the ceramic choke, and also I don't know, like making like some novel convection or no spreading system and convection system So I think there is some point of if there is a company or someone focused on this point, maybe in the future we can see like a printer, SLM printer for ceramics that directly prints ceramic without no need for either powder preparation or post-processing techniques.
Yeah. Thank you very much, Mohammed.
Not at all.
Okay, we can go on with the next presenter, Islam. If you are ready, this platform is yours. We can start.
He's not so far from Gökhan, in fact.
We are together here.
So hello everyone. Thank you, Gökhan, for introducing me. So I'm Bak Islam, as you know. I'm the ESR number 7, and I'm working on the design research and post-process optimization of calcium phosphate 3D printed bond substitutes. And I'm doing my research at Ceram. It's a Belgian company based in Liège that produce custom-made bond substitutes for maxillofacial surgery. And in today's presentation, I will start by an introduction, and after that, I will talk about the manufacturing process improvement that I performed in my PhD, and then I will talk about the bond substitute testing and all the tests that we performed on our scaffolds, and I will finish by conclusion. I will not share a lot of results in this presentation as it's confidential. But if you need to ask some question or know more about all the results that you get with the testing, you can contact me, or we can do another presentation with only our group. So as you may know, for most of maxillofacial injuries and bone loss or cancer, the surgeon needs to remove the damaged bone and replace it with replace this cavity with another bone or bone substitute. For the most used technique for this kind of application is the autograft, where the surgeon needs to take a part from a healthy bone and in the patient body, and then he needs to shape it and to put it to fill the gap of the removed bone. So this technique have a lot of good points, especially it brings especially the bone cell and the growth factor that are essential for bone healing. But it also had some drawbacks, and which are quite interesting for 3D printing bone substitute. So one of these drawbacks, we have the psychological sequelae that the patient could have after this kind of surgery, because of the lack of the aesthetical results in this kind of surgery, as you can see it in Adibia's face here, and also because of the long-term re-education and the rehabilitation that the patient need after this kind of surgery, because especially for the mandibula, for example, the surgeon needs to take a part from the fibula, which make it hard to the patient to work after this kind of surgery. And the most interesting part for 3D printing is that with this kind of solution, it could have a high cost because of the long time that you can have in the operating room, which is between 60 and 100 euro per minute, and which make it interesting to use 3D printing for this kind of solution. So the solution that's proposed by Ceram is called MyBone, and we only need to take the surgeon only needs to take a CT scan of his patient. He will upload the CT scan in our platform, and after some discussion with the surgeon, we will be able to define the volume needed for the patient, and we'll create the volume. And after that, we will integrate some porosity inside of it, and then we will print it and send it to the surgeon, and he will directly place it in his patient. So my work is focusing on the manufacturing of this product. So the design, the porosity design, and then the manufacturing process. So as I said, the title of my PhD is the post-process optimization and design research. So for the post-process optimization, we worked on the slurry optimization and also 3D printing parameters for the scaffolds. And we also worked on the cleaning optimization and the reducing of the time of thermal treatment time. For the design research, we choose scaffolds suitable for their use as bone substitute, and we mastered the design of these scaffolds, and then we studied these scaffolds by mechanical testing and biological performances. So in the literature, you can find that for pore size, it's recommended to have pores between 300 and 900 microns to allow cell proliferation and the growth of blood vessels. And this pore need to be interconnected to allow cell migration. We also need a pore shape, a concave pore shape to allow and to ameliorate the cell proliferation and the tissue growth. So based on this requirement that you can find in the literature, we choose to work on the TPMS structure, the triply periodic minimal surfaces that you can find in nature. So we choose to work on 3 different TPMS structure, the geroids, the Schwartz diamond, and Schwartz primitive. The most interesting part about this scaffold is their continuous concavity, as you can see it in the picture here. And also this kind of structure are generated going from a mathematical equation that help us to control the pore size and the wall thickness, which is a bit complicated, but can be worked with the design. So as a first step for 3D printing, we started with the design. So as I said, we mastered the design of our structure. So we are able to choose the wall thickness and the wall size of our TPMS structure. So the control of wall size helped us to improve mechanical resistance, and the control of the pore size helped us also to control the biological performances of our structure. So for the printing process, it's a vat polymerization process with DLP. So it's a layer by layer process. So as you can see it here in the picture, so we have the slurry that came from here and then is spread with 2 layer with 2 Dr. Blake. And after that, the DLP only send the image of the needed structure, and it goes on until having our 3D part. So for the 3D printing process, we worked on the time flash and also the energy and the spreading speed. I think that Chloe talked also about this kind of parameter, which are quite important for 3D printing with this technique. And we also worked on the ceramic, on the slurry composition, especially with the viscosity, to make it possible to print with a high loaded slurry to have quite a resistant ceramic part after the printing. So the next step is the cleaning. So after the printing, we get this kind of parts, which are green parts surrounded by slurry that we need to clean. And it's quite critical a step of 3D printing. So as you can see it here, we noticed first that we had a difference between the designed porosity and the real porosity that you get after testing. So this is due to a lot of parameters. So the first one is the design. As you can see it here, not only the control of wall thickness and pore size is important, but we have also the resolution that we can put on our design. So by putting a high resolution, we have a good part, but the issue is to process this high resolution, as it gives a big file to process in the 3D printer, which is make it a bit complicated. We have also a second point, which is the related to the 3D printing process, which is the light scattering, as you can see the result here. And the third point is the cleaning process. As you can see it here, at first we did have some part that's, we still have some slurry that is stuck inside of the part. And after the sintering, it densifies and it gives us a kind of dense part inside of our scaffolds. So for that, we decided to work on the cleaning process. That's I cannot talk about here, but we also worked on the design. So only by changing the design or the orientation of our geroid, we were able to have some continuous channel that allows us to clean easily the part. So as you can see the result here, it's quite good result. So after that, we have the thermal treatment. I worked on the optimization of the thermal treatment at Ceram. So first we needed like 5 days to totally treat our part with the debinding and then the sintering of the part, and we were able to reduce it to 3 days. So after that, as I said before, we studied our TPMS structure. So we chose the 3 TPMS structure, as I said before, and to study the effect of the pore size and wall thickness on the mechanical porosity, we chose to first to use a wall thickness to stabilize the wall thickness and to change the pore size. And after that, we decided to stabilize the wall size and to change the wall thickness to understand the effects of the wall thickness. So to study this TPMS, we have done the porosity test that gives the result that I talked about earlier. And we also have done 4 points bending test and also spherical indentation test, which is recommended by the ISO standard, but we cannot find it a lot in the literature. So we discussed this mechanical testing. And after that, we chose a porosity, the highest porosity of our scaffolds. And we decided to make a compression test with the 40 samples to be able to make some statistical tests on our mechanical testing. And after that, we have performed also in vitro evaluation to compare the 3 TPMS structure. So as conclusion, we are able we chose the TPMS structure for the study. We optimized the cleaning of the TPMS structure, as you can see it right here. We also reduced the thermal treatment from 5 days to 3 days of debinding and sintering. And we have a better understanding of the mechanical and biological performances of the TPMS structures. We also have done a world premiere with this TPMS with the CHU of Toulouse. It's the hospital of Toulouse, where we vascularized one of our bone substitutes to use it as bone graft for nose surgery. So we put this our bone graft inside of the forearm of the patient for 6 weeks, and then when we have the blood vessels, we took the blood vessels and the bone graft and we placed it in the nose of the patient. So for oral presentation, I've done a lot of oral presentation. You can see it here. And for the article, we submitted an article in the New England Medicine Journal of Medicine, and we have an ongoing article that we will submit soon. I would like to thank all of you at first, and I would also like to thank all the participants, all the person that participated to my project, especially the BCRC, where I've done most of my tests, and also the green mat that helped me a lot with all the powder issues and the slurry development, and also University Catholic of Leuven, where we performed the biological tests, especially Lisbeth Geris and Ehsan. So thank you so much. And if you have some questions, don't hesitate.
Thank you very much, Islam. For Islam presentation, we have a question, please.
I have one question, if possible.
Hello,
actually, congratulations, really, for the last results you shared. I think it was the most like physical, visible result in the project to be able to transfer it in a like biological sample. And I have two simple questions, like for 4-point bending tests, which kind of standard you follow? Because I was trying to make a 3-point bending test with BCRC, but we couldn't kind of deal to use what kind of size samples, because there are a couple of standards on like bending and also like in mechanical tests. What did you follow? Or
actually, we took a standard about technical ceramics because we weren't able to find any standards about the bending tests for bond substitute. We have only compression test and spherical indentation, but not the 4-point bending test. So we just followed a standard that the closest standard that we found about the bending test. And I think that is an ISO standard. I don't remember the number of the standard, but we adapted a bit to our process because the length of our samples, let's say with the DLP size, wasn't able to create the whole part and to follow exactly what is asked in the standard. So we modified it a bit. But yeah, it was really complicated to find a standard to follow for this kind of test.
Yeah. And another question: the 3D printed piece that you used for as kind of like a mold to grow this nose tissue, when it's transferred to face, like, are you planning to also transfer this 3D piece, or it was just a mold to grow the tissue and it will be removed and just the tissue will be transferred?
No, we needed this our bone substitutes for the nose to make the shape of the nose. So we transferred also the bone substitute to the. We also transferred the bone substitute to the nose of the patient.
Oh, okay.
To be able to create also the holes of the nose. That makes her able to breathe and to smell. So
yeah, that's amazing. Thank you so much.
I can add some more information about that. It's meant for the surgeon, they need to do some connection with the microvascular from the nozzle, which are previously put in the arm, to the existing nose. They need to do some connection for each. It's take a long time to do that. But it's a key point because the vascularization is very low in this space. And it's why it's very interesting to use this kind of materials with very nice porosity, which help for the vascularization a lot.
Yeah, it was really complicated. I think that it was Agnès Dupré-Bourrier, the surgeon that performed this surgery, and she used like 6 suture points on 1 millimeter. So it was quite impressive to make it possible. So you have the technical part, the 3D printing part, but also the competences of the surgeon in the surgery.
Yeah, it was a great result. Yeah. Thank you very much, Islam. Do you have another question? I think there is no question.
About your future? How do you see your future now?
For the moment, I'm with Ceram. So we have, how do we say it? I have a permanent position with Ceram, and I will continue to work with them because we have a lot of things to do, and it gives a lot of benefit to the patient also. So we can really see the result of the research. So it's quite interesting to work with them. So I think that I will continue with the company.
And maybe you can also explain a little bit what are the difficulty after the R&D part it could be the regulatory. It's very
yeah. It's actually it was really complicated to make research on the bond substitute in a company, because you have also always to respect all the regulatory part. So you cannot add whatever you want, and if you need to make modification, you have to be aware that if you make a big change in the product, you need to make a lot of biological tests and clinical tests. So it costs a lot for the company. So you have to be really aware about all the regulatory part to be able to improve a bit, just a bit, the bond substitute. And it was also quite complicated to, like, we can see a lot of ideas about like doping ceramics, for example, or making a big change in the ceramics. But when you are working in a company, you can see that this kind of stuff are really complicated to put in the market. So it was one of the most important thing and most critical thing in my PhD, I think.
Yeah. Thank you very much, so much indeed for your effort in this study. Okay, if you don't have another question for Islam study, then we can skip the last, our ESR 8. If he is ready, Asif, we can start.
I am Asif Rahman, ESR 08, and the topic for my presentation is effect of chamber dimension and laser parameter on SLS and SLM. So my main appointment was at Ermaksan, but we had some interesting collaboration with Gazi University, INFLPR, in Toulouse, and also University of Birmingham, and for the powder also at Marion Technologies. So I would remind for the project objectives, our project was for the centric chamber of the printer, and the mathematical modeling of heat distribution and temperature distribution simulations for SLS and SLM, and followed by the controller and the PhD thesis. So I would describe powder simulation of ceramics today, which we had achieved, and some temperature distribution simulation for selective laser sintering, and consolidation regimes in SLS, and the temperature distribution simulation for SLM, and 3 different regimes in the SLM process, and regarding the chamber, which we have achieved a little bit. So for the ceramic powder, because we were using for SLS a dry sprayed powder, this is very different from the metal powder or other powders which we typically use in the powder bed fusion process. It is a dry sprayed powder which actually breaks during the deposition. It's just like a snowball, you compress the powder. So it was paramount to see the breakage phenomena and understand how the powder breaks, and how we can optimize the layer for different powder morphology, powder size distribution, and several other properties of powder. So we using a uniaxial compression calibration method, we calibrated our discrete element modeling breakage model with the experimental results which were done in collaboration with another ESR, Pedro. So this you see here is our simulation calibration during the powder uniaxial compression test. So the compressive force is being depicted with different color. As the compressive force increases, the powder starts to break into smaller particles. This was the model was calibrated using the experimental results for hydroxyapatite powder. So here you see the blue line, which is the experimental, and the orange line is the simulation calibration which we have done. So in the real printing process, we are compressing the ceramic powder layer to a large degree. So sorry, I think it did not work properly before. So here you see the particle under the roller, because you are seeing in the particle scale. So the roller is looking too big, but is based on the experimental dimensions and the scale up we had done. So here you see some fragments of the broken particles. So only fragments have been shown here in this one. You see some powder under deposition. So the powder size distribution also changes before the powder layer deposition, and after the breakage it can change. So this was also calibrated using the experimental data. So this can give us very I mean optimization results for a layer. For example, if we want to optimize the powder size distribution for dry sprayed powder, so depending on the porosity and increasing the density with the different compressive mechanism, and if we change the roller speed or compression mechanism. So in this one, we model the basically the powder and the deposition method. After this one, we use the powder experimental details for simulating the process of selective laser sintering. So the process simulation was done for ceramics to understand the consolidation mechanism. A full field model was carried out, in which we explained different mechanism of ceramics. From sintering, premature sintering, when there is no interaction with the base plate, and when there is more than the laser is being penetrated under the layer, so it is completely consolidated, and there are thermal cracks also. And this was used to understand the printing of hydroxyapatite primarily with another in collaboration with another ESR. So we explained the different mechanism. For example, when the laser power is laser energy density is too low, we have very little interaction with the base plate, and the powder does not stick to the base plate, and this we named as a premature sintering. And similarly, when we increase some energy density, it has sintering, but it's also has good adhesion with the base plate. So this was also explained. So we explained in nice details of all the different printing regimes. For example, premature sintering, sintering, full consolidation, and consolidation with the base plate consolidation as well. So we gave these 4 different names based on the phenomena we experienced. So these are the experimental single tracks which we saw under different power of the ceramic selective laser sintering. In the SLM, we used a similar approach, but the powder is not dry sprayed for different metals as well. So we use the experimental powder size distribution to discretely model the particles, and after that we deposited the powder, and this layer was used for the full process simulation, and we explained the full field 3D model. So how in each instant and in each part of the melt pool in the selective laser melting process, the flow is behaving, and the velocity vectors within and outside the process. And we actually quantified the melt pool. So we described with the mass flow with the cross section in between. So how much flow is being pulled backwards and how much is flowing forward. So we described this in detail as well. So this was also verified and validated with the experimental studies. And similarly for preheating, we also simulated and described the process with the preheating at 500 and 1000 degrees centigrade as well. So we simulated the process and all the forces affecting during the melting, for example, recoil pressure, evaporation, and Marangoni flow, buoyancy, all these forces were explained in details, and the model was validated. And similarly, a full field 3D model was described with the experimental validation. So here you see an optical micrograph, and this one is simulation model cross section. So we defined a cross section in between, in the middle of the melt pool, and we calculated the mass flow going forward and going backward, because Marangoni is the main reason of melt pool instability. So we actually, when the laser is passing from here to the forward direction, there are several forces, for example, like recoil pressure, buoyancy, and Marangoni force. And because of some evaporation, there is a downward push, which is creating a depression zone. So to understand all this, we measured a mass flow being flown forward. So for example, when laser is passing from here to here, how much melt pool is flowing forward in forward direction, and how much in the backward direction was also quantified. So in the room temperature, this mass flow you can see in yellow and in magenta color. So the mass flow for forward is very little, but mass flow in backward direction is in large quantity when we are at room temperature. But when we increase to 500 and 1000, the mass flow flowing in the forward direction keeps increasing after the laser pass. So it has more time to stabilize. We explained this in details in our studies, and we described all three different regimes in different publications. So for example, a conduction mode regime in which the energy density is not too high, that it is reaching evaporation at that particular spot under the laser spot. So it is in the conduction mode, and it was also validated with the synchrotron study in this from the literature. So in this study, the tungsten nanoparticles were placed to see under the synchrotron how the melt pool is flowing. So it was well in correlation with our simulation model. Similarly, beyond, if we move above the conduction mode, or above, we increase the energy density of the laser, we move to a depression zone. So a depression is formed because of some evaporation that is being caused, and it is pushing the melt pool downward. So here you see the velocity vectors at different in the cross section, and only the melt pool without the powder. Here you see how it is being flown in at room temperature. This was also validated with the studies in the. This is, so you see here is our simulation models stream traces to describe the flow, how is being flown under the melt pool. So here is a study under the synchrotron from the literature. So this was correlated in this one as well. So we beyond, if we move beyond from depression mode and we increase further the laser energy density, how the laser can be, for example, when it moves inside the layer and there is some melt pool which is causing the penetration, and it can trap inside the laser irradiation. So there is multiple reflection involved, which is causing huge penetration, which is also being used for laser cutting as well in cutting mechanism, but this can also be caused when we have high energy density in melt pool. This one also was validated with the literature study here. You can see. So all these were described, and we also described some splashing, which is and spatter formation, which is caused when we have the instability during depression and keyhole mode. So you see how the splashes are formed. So we described this in details as well, and also counter-validated with the synchrotron studies from the literature. And for the chamber, we also came up with the deposition system, which for using for ceramics, and also we understood during our study that in the printing process the flow is not uniform. So for example, in the middle there can be a large amount of flow, on the different sides the flow can vary. So to come up with a very uniform flow all over the base plate or the whole printing chamber, we filed a patent to have a uniformity in the gas flow, because in the literature also it is evident that when we have higher flow speed, it helps in dissipating the heat and improve the printing process as well. So this deposition system was also filed for a patent. So we disseminated our studies in different venues. Actually, the binding mechanism for ceramics is in the pipeline with another ESR, Pedro, and the powder model still is in the pipeline, but we have published other, for example, the preheating and the full field model for the conduction mode, similarly for depression mode and keyhole mode. These were published in a different separate studies. For example, a spatter formation and also keyhole mode. And there were some studies with other colleagues, for example, from INF, LPR. Many collaborations were achieved, and we published all those studies. And we also have been fortunate to participate in some conferences. For example, Nordic Laser Material Processing NOLAMP in Sweden. We presented our conduction mode study, and also in EmergeMat conference for emerging technologies and materials, our paper for the depression mode and preheating received the best paper also award. And yeah, in collaboration with other ESR, we also participated in conferences. So these are some patents which we had filed for the powder laying primarily and the gauze flow. And during this, we received Young Scientist Award from International Conference of Emerging Materials at Institute of Non-Ferrous and Rare Metals, AMNR, in Romania, and the Viewer's Choice Category Award from the American Ceramic Society in the Creativity and Microstory competition for the 3D printing micrographs. And I have also served in the programming committee of American Ceramic Society, which is President's Council of Students Advisors. So they help in organizing different events like student competitions or others. So I served in the programming committee for 1 year. Yeah, this is the award we had received for Young Scientist Award, as I mentioned in the conference. And also in MSNT 2019, our micrographs received the viewer choice category award, and it was actually displayed on MSN during MSNT in 2019. Yeah, I would like to thank all the partners. It has been indeed a huge pleasure to work and collaborate with different institutions, and yeah, the generous funding from the EU and all the participation from all the members has been a pleasure also.
Thank you, Asif, for the presentation.
Thank you.
Is there any question for this presentation and study? I think there is no question. David?
Yes, Asif, I have many questions, but okay, no one wants to ask. Let me ask.
Yes.
You work also on the development of the new printer, and but it's a public. You cannot explain maybe confidential things. But what is the best improvement of your works, in fact, on the 3D printer?
My best contribution, actually, as you know, the roller patent was actually patented by a company. And so first challenge was a deposition system that can deposit the powder. So for all other companies that cannot use the roller, it was a big challenge. Yeah, overcoming this one was the significant contribution to the machine modification that can that was actually primarily for the metals. Now it can deposit ceramic powders. For the preheating, of course, it can be very helpful for the printing, because ceramics have less thermal shock resistance than metals and other materials. So this is one of the also very important factor that can improve, but adding it to the system actually needs everything to be new. So for example, our powder deposition system, which is the platform that is moving, if we move up to 200, there is no problem for centigrade with the motor, with the mechanism that is being used. But if we go beyond 500, so all the machinery is not capable of sustaining those, and there can be some issues with the motor systems and the deposition system. So this was actually a big challenge as well. Yeah, I hope this answers the question.
Thank you very much for this answer. I have another question about your future. What you expected to do? What is your situation actually, maybe?
Yeah, actually, as you know, I am based at Ermaksan is a company. I still have DOC-3D contract until 31st of December. So I am still working with the project. My PhD, actually, we submitted our defense forms, tried to submit in August, 2nd of August, but there was some issue that we faced, like some ECTs were missing. Credit hours. So I was in another city in the company, so I didn't got enough credits, because in some semester I was registering less. I didn't know about this requirement, and now in the next semester, which will start in February, we will register the ACTS, and we are going to submit the defense form and hopefully defend our thesis. So this was another surprising or shocking, I would say. Yeah.
Yes, but after end of December, you have a position in Erkmarstan?
Well, we are discussing this with the management, but until now I don't have a certain answer.
Sorry.
Yeah, please.
I am improving your communication. Hi, Tol. I am Ali Görür. I have also new in Ermaksan. I have been working here for 5 months. But in these 5 months, I saw that we have a huge library in terms of additive manufacturing in Ermaksan. In front of you, I would like to appreciate Asif for his huge contribution to us. Actually, according to me, we are lucky to have Asif in our company. Also, I am forcing our top management by Asif's help to convince them to add his into our organization.
Yes, thank you for your kind words. But I am still, I feel like a student. Yeah.
Is there another question? Thank you very much for your presentation, Asif. By this way, okay, on behalf of Gazi University, I would like to thank you all participants, because it was a good experience for us to join in the project under coordinator of David and management of Guillaume. Thank you very much for you. And after lunch break, we will go on to another presentation.
Yes, so
starting with.
I believe that it's now time to eat. And we will resume the meeting at a bit before 1:30 French time for the presentation of work package 345 and also the transversal work package 6 and 7, 8 as well.
Hello, everyone. We will restart this afternoon by the work package 3. The work package 3, we have 2 PhD students, and the work package 3 is led by University of Birmingham. And let me start to share the screen. Okay, could you see my screen? I hope so.
Yes.
Perfect. Okay. The work package 3, it's called Design and Product. And the research objective is to correlate input data to output produced ceramic and demonstrate it for application. And 2 OSRs involved in that. The first OSR, it's OSR 9. It's a resident garage buggy from University of Birmingham, UK. And the PhD thesis title is Development and Characterization of Multi-Compartment Ceramic by Stereolithography for Biomedical Application. And the supervisor is Artemis Stamboulis. And this PhD, it's performed in the University of Birmingham with the help of Litos. Litos, it's an Austrian company. Australia, it's a bit far from us. Okay. And we have a work package description. And from the OSR9, the project is delivered to a biomedical application. And we have a specific task for that. And the objective is to develop a ceramic 3D printed shoulder prosthesis and ceramic small orthopedic prosthesis that will have superior strengths for porosity similar to the natural bone. And the project will involve the following tasks: ceramic powder formulation with appropriate particle size distribution and morphology, modification of stoichiometry of ceramics to a thermally stabilized phase, effect of modification of the morphology of the powder and optimization, and the identification of a 3D processing parameter for optimization, including laser wavelengths, powder, or something like that, and power also. The second OSR involved is Aaron Osman from ENPT in France, and the title it's a direct powder bed selective laser sintering melting of zirconia-based ceramic and their assembly with metal as multi-materials. The supervisor has Ghislaine Bertrand, David Grossin, and Pascal Lenormand. And the work package description for this part, it's a task 3.2. The SR10 is developed to initially developed to aerospace application, but finally we shift to medical application. And the development of the ceramic 3D printing texture and structure and composite. We have a multi-component materials, and it will be used not for airflow and it translates for more for aerospace, but for medical field, it's more for osseointegration. And we would like also to do the control of texture and use of this composite structure for many applications. The objective is the development of the target system, the development of process concept of reaction from a composite texture, the printing substance to evaluate the textural capability, and the identification of 3D processing parameter and optimization, including the laser wavelengths, power equipment, and also a composite deposition, and also the assembly. For these two PhD students, Rezvan Garejbagi was not able to do the PhD defense because he's working in a UK company now. But Aaron Osman obtained this PhD in February 2022. And he will expose the PhD soon. We have a few deliverables and milestones with this work package. And it could be interesting for people which are outside the project to go online and to find information on the website or the European website. And you will be able to see the progress work package 3 report for each year. And for the last one, you will also receive some information about the final report. It's also public, but it's not yet finished because the project will finish at the end of the January. And you will not be able to find online for people which are outside the project for the PhD thesis manuscript. And we have 2 milestones, one on the Fab Lab demonstration, and one other milestone 11, which are shared with other work package, is to validate the design objective for medical and aerospace application. I think this presentation of this work package is finished from the macroscopic point of view. Because Rezvan Garejbagi is not here, and the supervisor Rezvan also, we might need to go to the, let me see, where is it? I think it's Aaron. Which, I don't check if...
yeah, that's probably gonna be me.
Yeah. And if you, I will stop to share my screen. If you want to share yours, it would be very nice.
Yes. I think I did it like this before. Sorry, it's my first time presenting through a tablet, so it will take a bit time.
Yes. If you have any difficulty, we can also share your presentation.
Can you see my presentation right now?
Yes, it's nice.
Okay, perfect. Hello, everybody, again. It feels quite nostalgic to be back together and presenting our thesis works. Today, I will be presenting a quite brief summary of my PhD thesis, which was focusing on the additive manufacturing of ceramic metallic multi-materials, which were fabricated by using powder bed selective laser processing method. So as quite fast reminders, when I started this PhD thesis, I took over a former PhD student, Loic Faraj's study, and the main objective was taking steps forward after his PhD. So in his study, he was focusing on optimization, parameter optimization for 8 biosed ceramic material, oxide ceramic, and it's very preliminary trials to combine with a metallic substrate, which is aluminum silicon 12 alloy. And after studying that parameters and getting used to the printer, the first job I did was considering an alternative to 8YOZ because we had some limitations with this oxide ceramic I will mention later. And after finding out a new alternative to this, which is alumina toughened zirconia, optimizing of the printing parameters was the next step. Once this optimization was done, I tried to combine this ceramic part with a metallic substrate, which is again aluminum silicon 12, because it was already tried before and I didn't want to like many steps at once. I wanted to go step by step, and that was the first combination. And then the main part of my thesis actually was a detailed characterization of both ceramic metallic assembly interfaces. So let's quickly jump to the results achieved in this thesis. So I mentioned about a material alternative to 8YOZ, which was, why it's not going, sorry, okay. Which was alumina toughened zirconia. The problem with 8YOZ was we were able to print solid, self-standing, manipulatable pieces with 8YOZ, but the problem was we were limited with dimensions. When we go for higher dimensions, we were stuck with fabricated size. We were having lots of deformation, so we needed an alternative for this. And also 8YOZ was only able to use for thermal applications, and that was limiting its target area, the application area. So first, I decided to go for 3 mol% D3 stabilized zirconia, as you can see here. But in literature, there was so many disagreement about using of 3YSZ for medical applications due to its low thermal degradation and some mechanical failures. So I came across to alumina toughened zirconia, which takes superior mechanical properties from alumina addition, and it's thermally more stable, and its melting temperature, as we can see here, quite lower than 8YOZ, so it's easier to process with our fabrication method. And its thermal conductivity is higher, which is another advantage in a process where we need to transfer high thermal energy in a very short time. So as an alternative powder, I decided to go with the same company because the fabricated powder was quite similar in terms of dimension distribution and flowability and layering. So final decision was for alumina toughened zirconia from Tozo. So even though these two powders are quite similar in their background, they are both D3 stabilized zirconia based powders, but still they are different materials and they need new optimization for this. And as their morphology and flowability and laser absorption is similar, I took the energy density needed for 8YSZ as a reference, as a starting point to determine new parameters for alumina toughened zirconia. So here there are lots of parameters tried, but I want to go to conclusion directly. So after trying parameter windows, I decided the energy density of 112 joule per cubic millimeter was the best results. I wish I could make an experimental design in this point, but I had like limited access to the printer. So it was a bit challenging to try like many parameters at once. So I decided to do a method like try and fail until I have a solid, well-standing pieces. And after that, I mentioned about the energy density needed for this, which is almost half of the 8YOZ, even though they are similar materials. And after that, I was able to print very solid, dimensionally accurate pieces. Even quite big pieces even takes like a long time. And also, which was very surprising, I was able to print directly without any additional step or any additional material, such as binder. I was able to print some pieces with inner cavities, which was the main achievement after this material change. So once I printed out the ATZ pieces, I combined them with aluminum to silicon 12 alloy. And the second and the biggest part of my study was to study the interfaces between material part and 8YOZ and the material part and ATZ. So why and how I call these parts an interface? What makes them different? The very first observation by Sam showed that in high magnification, both interfaces has a mixed phases coming from both metals and ceramic part. So I can say that right now because I know the further characterization results, but different scales and difference in the gray scale shows me the interface on this transition zone has different phases. So it gave me the first idea that can be my interface. So as a second characterization, I run an elemental mapping. And I studied 5 elements coming from both metal and ceramic parts, which are zirconia, aluminum, silicon, and oxygen. And also there is yttrium, but I'm going to show it later. So for let's consider the first interface. When I studied the location of existence of elements, I saw that zirconium coming from the ceramic part and the blue one, the silicon coming from the metallic part, they exist in the same locations, even though they are coming from different sides of the material. So the purple existency gives me the idea, okay, instead of just a physical bonding in between ceramic and metals, there is also a chemical interaction. There is a interaction interface zone in between ceramic and metal part. So what was surprising from this elemental mapping was no existence of yttrium, even though it comes from, it exists in the ceramic structure as a stabilizer, but it was not possible to detect any yttrium in the structure of the interface. So that was one of the main questions that I was trying to answer through my PhD. So of course, there were so many questions remaining. What's the depth of this interaction, even if I can see it in the SEM images physically, but is this the real interaction or it's wider or it's less? Where is the yttrium? And is there any phase changes after this chemical interaction of metal and ceramic parts? So I used 2 different methods to answer these questions. First, microprobe analysis and then the micro XRD measurements. And let's have a look for the microprobe analysis. Here you see the experimental profile that we decide. We decided to minimize the gapping of each study point when we close to interface, so we were able to detect more precisely existing elements. So here we see 2 interfaces, the first one up row and the second one. So in both interfaces, we can see the interaction zone, which is higher in the first interface and which is less thicker in the second interface. When we zoom in this interaction area, we can see that the elemental interaction zone is corresponding with the images that we see with scanning electron microscopy images. However, there is also penetration of other elements, for example, aluminum into the ceramic part and zirconium into the metallic part, way wider than, larger than this observation zone. So the first question was answered like, okay, we have interaction, it's quite visible in the SEM, but the elemental interaction is wider than that we see in the SEM images. So to detect these phases, actually to come back, we see that like yttrium is also not detected very much in the interface with microprobe analysis. So that's not a certain result says that we don't have yttrium, because the detectability level of elements in microprobe analysis around 4%, 8%. So it's not very healthy to say that, yeah, we definitely don't have yttrium. So we needed further investigation. Let's jump to micro XRD results. So for both interfaces, here you see the first interface. We see that there is an intermetallic phase between zirconium and silicon. Of course, the ceramic structure itself. and surprisingly, a ternary phase among aluminum, silicon, and zirconium. But microXRD is not enough to give you data about what kind of ternary phase is that. It just says in the data sheet, and also when you compare to other literature, it says this is just a ternary phase among aluminum, silicon, and zirconium. And we saw the same structure for the second interface as well. So we had to study more in detail in atomic level these interfaces to detect what are those intermetallic phases, what is this ternary phase, and what is the what's happening to yttrium actually. And for next, I used sorry, I forgot this here. I used the TEM characterization and doing like elemental mapping by TEM to go more in detail to detect yttrium. So here we see that for the first interface, for an example, in the yellow circles, we see that there are like silicon and zirconium existency where it's probably the ternary, the intermetallic phase exists. There is no aluminum. And also where we check the turquoise arrow, where we have like minor amount of silicon, zirconium, and aluminum, probably where is the ternary phase exists. And when we check yttrium and oxygen, we can see them, they're existing in dot-shaped areas, but localized in different areas. So when we come close to these dot shapes, we can actually see that, for example, here on the side, we have the ternary phase, where is aluminum, zirconium, and silicon. Here we have the intermetallic phase, where is silicon, zirconium only. And when we focus on inside of this dots, we find aluminum, yttrium, and oxygen, which is quite strange because we never observe any kind of phase including aluminum, yttrium, and oxygen. So when we compare this existency, as I said, we are able to identify these phases except this dot shape area. So the explanation for that, I'm sorry, I forgot to put the diffraction rings of this areas, but when we focus on the diffractionability of these areas, all these phases, they give crystalline diffraction rings, but when we focus inside of this circles, they don't give any crystalline structure diffraction pattern. So that means probably due to very high cooling speed during the process, something makes yttrium come out of zirconia structure, even if it's a stabilizer, and create an amorphous phase among aluminum, yttrium, and oxygen. So when we decide to identify, because here as well, sorry, the question was like still, what's the composition, real composition of this ternary phase? So we made a comparison and some calculation by using the lamella thickness from the TEM results and some data from literature studies which was done before, and the microprobe analysis to use atomic percentage of these areas where we detected by microprobe analysis. So when we compare this lamella thickness density and the atomic percentage of this existing elements, we see that this ternary phase areas exactly corresponding the structure which is seen here. So we also wanted to explain how this might happen. For this, we go to the ternary phase among aluminum, zirconium, and silicon, and we see that both the intermetallic phase and the ternary phase actually exist in the ternary phase. So when we put the atomic level in the ternary phase diagram, we see that we are somewhere here, and due to fast cooling and or other cooling mechanisms in the structure, we are able to actually obtain this area, and due to maybe quenching or another cooling trick happened in the structure, the phase can be like freeze, can be stabilized in this phase. So that was the explanation. Yeah, this type, it corresponds with our microprobe analysis results in terms of atomic ratio, and also it's possibly, it's possible to obtain in our ternary phase diagram. So to conclude quickly, I mean, I was not able to include all my results, of course, as all of us, but we see that after changing from 8 Viosset to 8EZ, we were able to overcome the size dimension limitations. We were more flexible with design, and we were able to obtain higher densities. And for the interface, we obtain a thicker interaction zone and also interaction zone and thickness for aluminum silicon 12 for 8 Viosset, and less thicker interface for the second interface. And for both interfaces, we obtain metallic aluminum and silicon, which is normal because the temperature that we need is very high for metallic printing, ceramic printing. So we decompose the metallic part, and we obtain both intermetallic phases and the ternary phases for both interfaces. So we can say that even though we change the material, our chemical interaction in the interface is quite similar with different thickness and interaction depths. So what can be done for future? Actually, we had preliminary steps of this characterizations. I wanted to make a mechanical test in terms of like compression, tensile, and 3-point bending test. And also for multi-materials to measure the adhesive forces between metallic and ceramic, I wanted to make a 3-point bending test and the shear test. But unfortunately, we were not able to do that in terms of time. And we really wanted to make the imaging of thermal interaction between the laser and like in situ thermal measurements in between the laser and the powder bed. And also trying new combinations for both metal and ceramic, for example, including titanium or cobalt chrome-based alloys for metallic part and other stabilized type of zirconium or alumina for the ceramic side. So here you can see the conferences I've been participating both physical and online so far. And in terms of papers, we published a review with Giovanni, Alejandro, Pedro, and other participants from DOC-3D printing, but we are also have like 2 papers ongoing, like hopefully publishing quite soon. So thank you for your attention. I hope I didn't keep it so long.
Thank you very much for this nice presentation. It's time for question, and we have a lot of time. Don't hesitate to ask a nice question to Erin. Oh, you are shy. Because we did not discuss about that during this presentation, maybe Erin and other, you can explain what was the impact of the COVID on your work, maybe, and what is also the opportunity with COVID.
Did I unshare my screen?
I can do that if you want. I will share. And,
no, but I want to share it, but I just click somewhere else.
Okay.
Okay. So I think you were asking what was the major impact of COVID during the process. Yeah, I mean, we all of us, I think I can talk for everybody because of like we were in contact all the time. And when we had this supervisory board meetings for especially last year, it was the main concern from all the ACRs about like their delay or accessibility to their labs, blah, blah. But I mean, the main problem was, of course, the time. Everybody had to delay their especially experimental studies. For me as well, I was quite short in time to especially catch the mechanical characterization because I had to do the first things that I was planning for the first and second year, and I had to do them for the third year sometimes. And I think another biggest drawback from COVID was networking for everybody, because everybody managed to find a way to finish their projects, and I think all of us we have like very beautiful results, very good contribution to the scientific area. We can see them from the feedbacks in like international conferences and everything. But everybody was so tired of this like online conferencing and disappointments of like just last minute changes and everything. I mean, I don't even remember when was the last time I saw everybody together. I think it was in like Mabesh for the first DOC-3D printing. And then some of us, we saw each other for the conferences, but it was never this, we always had this soul of like DOC-3D printing, but physically it was very hard. But I think we did a good job with your understanding, because I think also that most of the supervisors, they were like very understanding about the delays and everything, because it's out of our control. So
I hope so.
But I think that we had also some opportunities with COVID, because I think that if we hadn't the COVID, we weren't able to participate such number of conferences and webinar. So I think that's it's a good point, and we have to say it's also.
Yeah, that's true. Yeah, definitely. And we were able to have some extension as our studies, so it was also nice.
And if someone would like to ask a question to Irene, it's a good time for that. If not, I have a question, maybe. As if you want to ask a question.
Yeah, I want to ask, did you try some heat treatment as well?
No, because the thing is that to try a heat treatment, for example, like, I'm sorry, I'm just a bit sick. To try a heat treatment, I needed to develop a strategy where I can treat the ceramic and metallic part at the same time. So, for example, when I was using both type of oxide ceramics, zirconia ceramics, to apply them heat thermal treatment, post-treatment, I need to heat them up to like, let's say 700, 800 degrees to reduce the cracking pattern. Then the metallic part was going to be melted completely. And another main objective of the study was like directly print out these ceramic parts. So I was not very huge fan of like applying a thermal post or pre-treatment, but of course that's the solution for the interface for the cross-section studies, because we saw lots of cracking.
So in the process, did you analyze some phase changes? For example, you showed the ternary phase diagram. So during the process, for example, for the ternary phase, sometimes the density is different.
Actually, for the 8YOZ, it always stays in the cubic phase of zirconia, even before and after, because I compare the XRD patterns of the powder and the printed pieces. For 8YOZ, it was always the same, but for the 8EZ, I think it's due to the existence of alumina inside the zirconium structure. At the beginning, for the powder, we had a tetragonal phase and monoclinic phase, but for the ceramic pieces printed, we only had tetragonal phase. So there could be like two explanations for this. Maybe the monoclinic phase kind of turned to an amorphous phase and we cannot detect it by XRD, or due to a phase transformation because of the heat, or as I said, the existence of alumina, because it locks the boundaries of monoclinic grains. It's kind of turning all the monoclinic phase into tetragonal phase. So short answer is like, yeah, I observed phase transformation for 8EZ, and I didn't observe any for 8YOZ.
So there were any strange behaviors during your different parameter testing? For example, sometime you have a huge jump in phase, another time there is less same phase for different parameter, or like this?
Actually, I didn't observe any like extreme change. Of course, results were like something new. We figured out some changes, But
I am
actually,
asking because, for example, for alumina and magnesia, I did the printing, and then I mixed physically alumina and magnesia, and there is a phase aluminate MgAl2O4. So in some XRD results, I was seeing too much. In some, it was very less. So I was thinking whether you saw some similar behavior.
yeah, because for example, to make XRD measurement on printed samples was quite challenging because you don't know what you have where. Like, for example, on top of the final layer of your surface, it's connected with the air, so it can be a new phase. Or if you, for example, grind your piece and bring it a powder form and do an XRD measurement, probably you will have something different. But what I did was only like measuring the top surface and the cross section, the middle of the piece on a solid piece, and I didn't see any like awkward behavior that much. It was just a phase transformation of the zirconia.
Right. Okay. Thank you.
Yeah.
Okay, thank you, Asif, for your question, and Aaron for the answer. I still have one question. Maybe, Aaron, if you can explain how much is easy or how much is hard to change from one product to another. Because many people in this field would like to change that to another material, but maybe you can explain it a bit.
Yeah. Actually, it depends in which area you're working on. For example, if you want to go powder change for a metal, I think it's rather easy because there are lots of studies. You know what you expect, what you can see, or you can compare results, or you can see other people's trials before because there are lots of studies on metal additive manufacturing. So you can see, like, you can even have the parameters that are working for them. But when I started working on like powder bed selective laser processing on zirconia, there was just Loic's study and one or two more other studies for like, it applies for all of us actually. So my main approach was like, yeah, I knew that I need new parameter optimization, but my goal was improve it with a logic way. For example, addition of alumina, because alumina is mechanically more stable, it has more phases. So if I can track the phases, I can see which temperature gap we are reaching. And it was not easy, but not hard as well. It was just, I needed to do it because we had to step forward. So alumina toughened zirconia was the most logic candidate. And actually applicability also very important, like supplyability is also very important because yeah, there is studies showing that cerium stabilized zirconia is amazing. It never thermally degrade. It's perfect, blah, 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 blah. It's much better than everything. But 1 kilogram of cerium stabilized zirconia is like 100,000 euros. And I need minimum 2 kilograms of this powder to start the test. So it's not applicable. I know there is better options, but I cannot supply it. So that was the most logic and easy to supply option for 8YOZ replacement.
Okay, thank you. Maybe if you have a question?
Yeah, question. Thank you for your presentation. You did good job, Aaron. What's your idea about if we tried to produce this method using direct energy deposition instead of powder bed fusion technique? It would be better. Do you have any idea? There's another technique, do you know? And you know, they produce some tracks and porosity structure, but for mixture, maybe it would be better for this aim.
The thing is that during my PhD, I did a microsecondment with a company called Optarn, which is also our partners in the project, and they have a direct energy deposition machine. We tried our powder and we tried to optimize lasing parameters. We were able to sinter and consolidate my powder. However, it was very hard to attach it to the surface because there is a nozzle, like the powder comes, the laser processes it, and it kind of like eject the powder, this like fuse very fast to the surface. So that makes the ceramic paste or this processed ceramic jump back and get lost. So that was the main problem. Like we were not able to deposit the ceramic melt on the metallic platform. And also another problem was, yeah, you can do it with a 90-degree nozzle angle, but as you are using a metallic platform, the high laser radiation can go back to the machine and destroy your machine. So because of that, you need to work with an angle. So that makes the ceramic go to the surface and split again from the surface. So it was very challenging to have a stable 3D object on the building platform. But I think it can be developed. Yeah, it can be developed.
Thank you very much.
You're welcome.
I still have one question again, but initially the project, the plan was to focus on aerospace or aeronautical application, and you shift to medical. Maybe you can explain why you want to shift and what is
Yeah, as I mentioned at the beginning of the process, the presentation, I had lots of dimensional limitation with 8YOZ. So we were able to only print small size, let's say 1 cubic centimeter pieces, the maximum, which was not even that big. So I needed to find an application area which I can only use like small applications. So dental area was the best candidate for this because zirconium is used there, and you just need to study like small implant dimensions, and that was the main idea to go there actually.
And you choose also specifically a dental application. I see.
What do you mean?
I think because it's existing many field in medical, but I think
because I mean, again, due to the size limitation, because for a knee or hip replacement you just need like big pieces, so it was like quite challenging to produce that pieces. And actually when you check a dental implant structure, you don't need so much complexity. You don't need any inner cavity, you don't need any hanging structure, for example, or inner holes mostly. You just need a dense solid material.
Thank you for this nice answer. I don't know if someone wants to ask a question. Sorry, I have a lot of questions for every people.
It's okay. If you have time, I'm here to answer.
No, but I think we can shift maybe to the other work package.
Okay.
And I think I am the coordinator of the work package 4. Sorry, I just forgot to mention for the work package 3, the work package leader, it's Artemis Ruiz, but she will be not able to connect, unfortunately, for technical issue. But maybe she will try to be here soon. Let me share the screen for the work package 4. Okay, I hope you can see my screen. I will try to put in full screen. Is it working? I hope so.
Yes.
Yeah, it's perfect.
Oh. And the work package 4, it's on testing and standard. And the research objective is to define and establish standard and standardization and regulatory issues, and the qualification and risk analysis. We have 2 PhD students, and I will start by the first slide. It could be very accurate like that. And the first PhD student is Alejandro Montanzaga, and he works on additive manufacturing of silicon carbide-based ceramics by powder bed selective laser processing from the functionalized powder to the final part. And it was supervised by me and Francis Marie. And we work also in PT, but with the company Mersen Bustek, and with the help also of Gazi University especially on the modelization with the moment. The second OSR is Ambra Patalini from the company Linkotech in Italy. And he works also in the university, she works also in the University of Birmingham and with the company Litos, and many characterization is performed in PT in Toulouse. And the title is a lithography-based ceramics manufacturing of semi-porous orthopedic implant, printed part, tribology and design of a finger joint prototype. And the supervisor are Artemis Tamburis from University of Birmingham and Maggio Piccinini from Linkotech company. If you look the work package description, we have two tasks, and the project is developed on the standard and regulation for medical sector. It's a task 4.1, and the task 4.2 is the same but linked for space sector. And one objective is to do a mapping of relevant standard concerning 3D printing technology, and to reference material standard and regulation source for biomedical application and for space application, and to develop a new standard concerning 3D printing technology, and to work on all predictability studies, durability, and critical analysis. And for these two students, Alejandro Montanzarazaga obtained his PhD in October 2021, and Ambra Patalini in January 2022. And for this work package, we have a lot of deliverable milestones. Like I said previously for work package 3, it's a public report, and you can find for the last years also a final report which are drawing. It will be available at the end of the project. We can find also the two manuscripts, but it's confidential. But in practice, you can find it online very easily, I hope so. And we have also one specific deliverable on the standardization regulation, progress review and evaluation, which are public, which explain what is the current status for many standards and what are also the main hot topics. And one milestone is focus on the validate design objective for medical aerospace application. This milestone is shared with the package 3. I think we can start to listen to the PhD student on this work package. And I would like to invite, I think it's Alejandro Monton, the first one. If you want to share the screen.
Yes, I think so, David. I would. Can you see my screen?
Yes.
Okay, let me 1 second. I will close the door just in case there is some noise.
The stage is yours.
Okay, thank you, David. Thank you for the interaction. So today we'll talk a bit about the results we have seen in my PhD work, direct powder bed selective laser processing of silicon carbide. I am Alejandro Monton Zarazaga, and my supervisor were David Rosan, Francis Marie, and also Marc Ferrato was involved because he belongs to Mersen Bustek. So as a reminder of the project objectives, first of all, the material that we use for this PhD work was silicon carbide. I won't enter into details, but you probably know that silicon carbide, it's a ceramic with excellent properties, such as very good mechanical properties, chemical stability, and is used for a wide range of applications, especially for aerospace applications. For example, Mersen Bustek is focused on, I would say, more than 80% of the industry of the application of Mersen Bustek is focused on aerospace applications. So here is the powder that we use. We use different powder sizes, but in general, for the additive manufacturing process, we were using this provided by Mersen Bustek. It's the same silicon carbide powder that they are using for the industrial application and industrial processes that they have. And mainly, I won't enter into details because they already explained the technique and so on. we were using powder bed selective laser processing as additive manufacturing technique in this PEC work. Typically, as you know, this technique is called selective laser melting, selective laser sintering. But we wrote a review explaining that for us, it's more interesting or more appropriate to call this technique as powder bed selective laser processing, since in this kind of powder bed processes, you don't find just melting or sintering, because both can occur or even more phenomena. So here very fast, just in case you didn't attend previous presentation and so on. Here we have the powder. The powder is dry. So this powder is puffed into a thin layer. And here the laser scans selectively the pattern determined by the software of the computer. And this is repeated layer by layer until the wall form, the wall part is manufactured. So typically for this kind of additive manufacturing techniques, powder bed selective laser processing, there are two different approaches. Non-direct approach. Can you see my mouse or not?
Yes.
Or like this is better.
Yep.
Okay. So typically we have two different approaches, like non-direct. Here we have to mix the initial powder with some binders. And after treating with the laser beam and laser processing, we obtain what is called a green body, green sample, and some sintering debinding is required. On the other hand, we have direct approaches, where sintering and debinding is not required. However, this process for silicon carbide is very challenging because silicon carbide has not a liquid phase under normal, let's say, circumstances, as you can see here in the phase diagram, but instead decomposes in excess of 2,545 degrees Celsius. So it's a very challenging material because we cannot, let's say, use this technique as typically is used in metals, like liquefying and resolidifying the material to get the 3D parts. So let's say before this PhD, and even currently in some companies, the technique or the approach that was used for direct methods was to mix the silicon carbide powder with some silicon powder. So after the powder bed selective laser processing, you were obtaining a porous silicon carbide preform that after some phenolic resin infiltration and some liquid silicon infiltration, you were obtaining a reaction bound silicon carbide part. But this is not a real, let's say, silicon carbide part, because when you get a reaction bound silicon carbide 3D part, you decrease the mechanical properties compared to just silicon carbide. And moreover, typically you have some residual silicon content. So for some specific chemical applications, they are not suitable because you need ideal, let's say, chemical stability, and with some silicon content, it's not possible. So what's the original scientific approach of this PhD? What was the, let's say, the main idea? So here, instead of using this, let's say, mixing of silicon powder and silicon carbide powder, what we are going to do is to graft a pre-ceramic polymer on the surface of the silicon carbide. So this, after the laser processing, we will obtain a body of silicon carbide, a part of silicon carbide. So here, let's say the secret, the key point is the nature of this pre-ceramic polymer. Basically, this pre-ceramic polymer, after some heating, will create a stoichiometric silicon carbide coating via high temperature treatment in inert atmosphere. So let's say that this grafted molecular layer will create a reactive interface between the silicon carbide grains of the powder, which facilitates diffusion and sintering. At the end, these particles will be bound together, and we won't affect to the final material phases because this pre-ceramic polymer will be part of the final structure of the silicon carbide, and it will be converted into silicon carbide. So the main objectives of this PhD work can be divided into four. So first of all, before starting with this idea of grafting this pre-ceramic polymer to have a direct method, we decide first to optimize the process of PBSLP just by using silicon carbide. So here, Mohamed already explained many stuff about the optimization and so on. Thanks to them, we create a very nice collaboration with Mohamed and with Goham. And it was very useful because we were able to study both numerically and experimental, all the parameters, and be able to explain how they are affecting, how they can be optimized and improved. So there were 3 key points to optimize this process of direct powder bed selective laser processing. The first one was the laser material interaction. After, the powder flowability and bed packing density. Here we have more limitations since we were using the same powder provided by the company, and we decided not to modify it to keep it equal to the one used for the industrial processes. And finally, we studied the laser parameters and scanning strategy. Here I won't enter into details because Mohamed already explained everything about this. So next, after optimizing the process of additive manufacturing of silicon carbide, we obtain very nice parts with, let's say, relatively high relative density. We decide to study the original scientific approach of this PhD that we already explained, the powder surface modification. So here, what we were doing was to optimize the grafting process of this ceramic polymer onto the surface of the silicon carbide powder. So for that, we were using a ceramic polymer, commercially known as CVD 4000. This is a carboxylane oligomer that typically is used for CVD process to grow silicon carbide coatings. For that, we had to use some solvents. We had to use some post-drying steps. We had to optimize the amount of the ceramic polymer, since if you were using an excess of this ceramic polymer, you were obtaining a lot of agglomeration, a bad grafting performance, and so on. So after all these steps, we were able to optimize this grafting process and obtain a good quality of the powder, and very important, without affecting to the powder flowability. Otherwise, we would have some issues during the additive manufacturing process, since we need a very nice powder flowability for this kind of techniques by using the dry powder. So next, after performing this grafting, instead of testing directly this modified powder with additive manufacturing, we decide to study the sintering behavior of the modified powder with a very well-established and well-known technique, which is spark plasma sintering. So here, what we were doing was to compare the sintering of the silicon carbide powder and the sintering of the surface modified silicon carbide powder. So here we observe 2 different, let's say, phenomena. First of all, we obtain a very nice reproducibility of the parts, and we got 91% of relative density for the silicon carbide powder and 96% of relative density with the surface modified silicon carbide. That means that we were enhancing the sintering behavior of the silicon carbide powder by using this surface modification. And moreover, here I didn't write it, but we observed too that the sintering, the temperature where the sintering was starting was almost 200 degrees Celsius below than the powder that was not modified. So after this, after optimizing the additive manufacturing process for silicon carbide, performing the polymer grafting, studying the viability and the behavior of the sintering of this surface modification, and checking that it was improving, we decide finally to use this modified powder in additive manufacturing, specific powder bed selective laser processing. So here, similar again, we compare the silicon carbide powder and the surface modified silicon carbide powder with the PBSLP. So here, I will try very brief to explain what's the mechanism of the, let's say, the improvement of the relative density, because we observe again that with the surface modification, we were improving up to 10% the final relative density of the manufactured part. First of all, we had a thermal decomposition due to the laser radiation. Due to the laser radiation. So, in consequence, the grafted ceramic precursor was losing hydrogen. It was creating cross-linking and at the end, a solid amorphous polymer. So with this laser treatment, the loss of hydrogen was continued, creating some cross-linking, creating a solid amorphous silicon carbide that after was converted into polycrystalline silicon carbide. Here we know that this ceramic polymer was converted into polycrystalline silicon carbide because before this work, Francis Marie with another PhD students was using the same CVD 4000 polymer for coatings of silicon carbide for CVD applications, and they checked and studied all this transformation. So after this grafted molecular silicon carbide hydrogen was creating a reactive interface between the silicon carbide powder grains, facilitating diffusion and sintering. Because probably, as you may know, if this polymer is converted into amorphous silicon carbide, this is facilitating the diffusion and sintering because it's amorphous. So at the end, we were bonding ceramic particles without affecting the material phases. So the debinding process was unnecessary, and all the polymer oligomer was converted into silicon carbide. So this ceramic polymer at the end was in the final structure of our 3D part, and moreover, it was converted into polycrystalline silicon carbide. So at the end of our PhD, the most interesting results that we achieved is after all this process are these two, because we were able, I would say that at least regarding the literature for the first time, without using any kind of silicon and so on, to create very complex shapes with relatively high relative density, up to 81% of just silicon carbide. So for example, for this part, this turbine of 2 centimeters by 2 centimeters, it was taking 2.5 hours. And for this lattice structure, as you may know, for the moment, I think just can be manufactured by additive manufacturing. These are whole inside, it was taking 3 hours. So to conclude what we were doing in this PhD, first of all, we were studying experimental and numerical, the direct powder bed selective laser processing in collaboration, as I told you, with Mohamed Agoha and Goham with Gazi University. So after this optimization, we studied the ceramic polymer grafting. Then we study and optimize, of course, the sintering behavior of this surface modified silicon carbide. And finally, we repeat the first step, but this time using the surface modified silicon carbide. So as publications here, if I remember, yes, we wrote 5 publications. I would say that this one was the first review ever written about selective laser sintering melting of technical ceramics with Pedro, Eren, Giovanni, David, and so on. And moreover, here I didn't write it, but we are still expecting to publish one more article. So that means that we would publish at the end of this PhD 6 articles, which I think is very nice. So thank you for listening, and I'm open to any questions you may have. Thank you so much.
Thank you, Alejandro, for your presentation. It's time for question.
David, I have a question or a comment. Yes, I think that Alessandro, you have to insist that it's very difficult to sinter pure silicon carbide, and usually they use additive sintering additive. Okay, thus your polycarbosilane help because you explain by the mechanism. Okay, but if you want to increase the density, perhaps you can use a polycarbosilane graft with boron. There was a thesis in Limoges this week. Thus in Limoges, they are able to graft boron on the polycarbosilane.
Yes.
And then perhaps, yes, you can contact Samuel Bernard. If you want to continue on that, perhaps you can test the technology with boron graft on the polycarbosilane. That's a suggestion.
Yeah, for sure. It's a pity that we had to stop this PhD work, but there is an end for everything specific for the PhD thesis. It's true that with more time, probably another possibility was to study boron carbide, because boron carbide is mainly used for industry as additive to even enhance more the final densification of silicon carbide. So yes, this could use more or less the same idea. And for example, something that we didn't have time either was, for example, to create or to use some infiltration of this polycarbonate. But honestly, for industry, I could say that now this idea of, for example, infiltration of polycarbonate is not very interesting because it's very expensive. It's very, very expensive. So yes, it's a pity we had to stop. And I would say that still we have some difficulties in terms of achieving high density, because the powder that we use is, let's say, big for this kind of sintering applications, because we cannot use powder smaller than 20 micrometers. That, for example, if we compare with nanoparticles and so on, we could achieve more high relative densities with other processes like SLA or robocasting. It's a pity that now there are other solutions. For example, now there is a technique called LIS, laser-induced slurry deposition. Instead of using this powder bed with dry powder, they are creating some kind of slurry. And it's similar, but at the end, they obtain a grain body. But after sintering, they obtain very, very high relative densities of up to more than 95%, I could say, for silicon carbide.
Okay.
Thank
But
you.
yes, I agree with you on silicon carbide is very difficult to sinter. Yes.
I don't know if we have another question in the virtual room or in the physical room also. But...
Yeah, I have a question. What is your opinion about using different spot size for laser for printing silicon carbide?
Honestly, we didn't try because, as you may know, for example, that we were interested to study, but we are limited to the 3D printers that we are using. Of course, by using a small spot laser, you could have more resolution and you could able to control even more your process. But you know, sometimes it's something that you cannot choose. You have to work with the machine that you have. So that's it.
No, for the small spot, is it not more difficult to print?
With a smaller spot size of the laser?
Yes.
You should be able to even control more the process, because, you know, these kind of lasers, they have a Gaussian distribution. So the smaller they are, the smaller is also this distribution. So you could even control more the heat that you're affecting to your material. It's true that it could be slower, but for sure you had better resolution and better properties at the end.
So did you have any opinion about using the overlap? How much overlap we should use for silicon carbide or for different scanning lines of laser?
Yes, the overlapping, it depends on the materials that you're working with. For example, we were using, let's say, minimum overlapping, because it's true that we observe if we were not using any overlapping, you were not affecting to your previous treated, let's say, powder bed, and you were not able to sinter properly these two parts. So that's why we decided to have the minimum overlapping. Now I don't remember the number, but probably it was equal to the powder size that we were using to, let's say, excitate again these particles that you treated before and be able to sinter with the new particles.
So do you think power has more effect or speed has more effect on the printing?
I would say that here for ceramics, it's very important to use slow speeds, because as you know, sintering at the end takes time. So it's true that for me, sometimes the value of irradiance is not the best one to work with, because it's true that you can have the same value of irradiance by modifying, for example, very high power with very high speed, but at the end, the process won't be the same.
Okay. Do you think it will ever reach a full complex part of printing with laser for silicon carbide particularly? Do you think there will be?
Yes, if we are able to reduce the powder size that we are working with, we will be able to do it. It's true there is another issue, that it's powder flowability. If you have very, very, very small particles as nanoparticles, it's very hard to get a nice powder bed. So that's why, for example, now researchers decide to work with slurries instead of dry powder, and they are getting very nice results.
Also, it's
But
cheaper,
will...
very cheap to use slurry.
Yeah, but at the end, they don't have a direct method, which makes it more expensive because you have to sinter your sample at the end with a furnace again. So it's something that in the future, I think it will be possible. I don't know if with very high relative density, but at least for some porous applications, for sure.
Nice. Yeah, thank you. Thank you for the nice presentation.
Thank you.
Yeah, thank you.
Okay, I don't know if we still have a question. I have a question, in fact, because I think Alejandro, you organized with other PhD students, with Aaron, Pedro, and Giovanni, ICAM, and I think it was very pleasant to do that for you. And I think last time when we discussed, you would like to create some kind of continuation for the school on additive manufacturing. I don't know if you want to say a few words on that.
Yes, sure. In fact, the last YCAM in Barcelona with David, I was discussing with him that I think that it could be convenient to keep the additive manufacturing workshop, the ESERS additive manufacturing workshop that we organized before for your YCAM. I don't know if you remember. And basically, this year will be a bit different because, as you know, Nico and I both are part of YCM, the Young Ceramics Network. We are in the committee. So for the YCAM organization, now YCM will be involved too. So both Nicola and I will be involved in the YCAM organization. So in parallel, I would like, as we did it before, the day before or 2 days before, to organize and create again this additive manufacturing school. So if you are interested to collaborate with me and Nicola or everything, I think we could do very, very nice things. Because honestly, I think that the network that this project created in terms of additive manufacturing of ceramics, it's great. And we could organize very nice events with students and young researchers.
Yes, it's perfect. Nice.
Alejandro, do you have any event coming organized, or you're just talking general to join you?
We want to organize this additive manufacturing school prior to YCAM, that it will be next year. So I am just open to anyone who wants to join us to help to create this additive manufacturing school.
Oh, okay.
This school will be in Ankara, or?
No. We'll be in the same location of YCAM. We don't know yet. So this is like a parallel event. Typically, YCAM is from Wednesday to Friday. So as we prepared before in Toulouse and so on, or even in Barcelona for YCAM, this additive manufacturing school will be just the day before or 2 days before the YCAM in the same location, same venue, and so on.
Right.
Because as you know, YCAM typically is focused for young researchers and young students. They present PhD works, master works, but typically we don't have a lot of, let's say, senior researcher or professors giving some talks. Typically we have maximum 3-4. So we would like to have like more experience in these additive manufacturing schools, as we did before, guys. It's exactly the same idea. And even we thought about having some kind of real activities. I don't know if by having a 3D printer with us and optimize some powder, something. After we will do some brainstorming to get more ideas. But first, I would like to invite you if you want to collaborate in the organization of this school. Because we did it already with Pedro, Giovanni, Eren, David, and I. Yes.
And what you can help also, it's because often the YCAM committee they ask to have some financial support from the JEX trust, okay, and we have also agreement with the American Ceramic Society, for instance. Thus, and sometimes the American Ceramic Society can give some grants to American students to come to Europe. Okay, and we did the same to go, for instance, to Daytona, where Nicola went, and so on. Thus, perhaps as you will be in Atlanta, perhaps you can did some dissemination when we will know the place, YCAM and the date, and perhaps to try to incite some American students to come to this event in this school and the YCAM.
Yeah, that's actually a great idea. So I will follow the ISAR's calendar and I will be with Nicolas all the time. So when I see that the dates and the place is coming clear, I can definitely help to create this kind of bridge to bring some like American students to Europe.
Okay.
It will be maybe in September or the end of August. Yeah. And they already know the place, but it's still a keep secret. Yeah.
Ah, okay.
Alex, I think that I would like to participate and to help for this kind of event.
Okay, thank you, Islam. I will think about it. I'm kidding, for sure you're inside.
I think I will give also my support and help for that, but I think it would be nice if it could be led by you, the young guys.
Yes, it's very nice, I think that we want to keep that atmosphere.
Not very young anymore. I think I'm a little bit more close than Santa's and young guy.
Yes, I'm happy to see that the idea we had when we organized the first school in Maubeuge, that was to combine with the YCAM, remember, and to invite other than the ESR for the school, and yes, very nice. I'm very happy the evolution of that. Thank you also to Nicolas who helped me to organize that at that time.
Yeah.
But for sure, it could be nice also to organize sometimes something in Ankara, because we miss Ankara.
Why not? Yes.
During the COVID, but maybe one time we'll be able to do that.
And Bucharest also, yes. Yeah.
Bucharest also, yes. I don't know if we still have questions. I see I have one question, and I think I forgot to ask to Eren. But normally we ask, what are you doing now, and what is your future? And if you want to do that, Alejandro, and then I will.
Shall I start, or it's Eren? Eren, you can start if you want. You work first.
I think it would be better to start, Alejandro. I think.
Okay. Yes, probably it's better. Yes. So after finishing my PhD, before finishing my PhD, I was offered a position at Georgia Tech, where Nicola is right now. So even before finishing my PhD, I knew already I was going to Georgia Tech to continue with additive manufacturing of ceramics. Nico already explained a bit the concept, but there we are working on new pre-ceramic chemistries to have some additive manufacturing process of ceramics at low temperatures. So after I joined Georgia Tech in November, so in the beginning of September, I was offered a permanent position in my hometown in Zaragoza. It's a company. Well, it's a group of companies. It's huge. There are more than 6,000 employees. So I was offered here in the part of the Research and Development Institute permanent positions to work of research and development of ceramics. So here I am in my hometown, finally happy with my family, my girlfriend, my friends, and working on ceramics. So I can be happy right now in these terms. Yes.
Okay, thank you. Just I suggest to start by Alejandro, because it could be a little bit easier after to cut and to put Eren part to the.
Yes.
But Eren, if you want to explain what you are doing and what is your expectation for the future.
Yeah, actually, after finishing my PhD studying last February, I was a bit busy with becoming French, having the nationality. So it was like tons of paperwork, but finally in August, I was able to obtain everything that I need. And the timing was quite accurate for all of us, because Alejandro was leaving his lab in Georgia Tech, and they were like looking for someone new, and I get in contact with their professor and Professor Losego now, like we are working together. I just got my visa like last Wednesday, so in a couple of weeks I'm going to Atlanta to join Nico, and we are gonna be working like very parallelly. And mostly the topic that I will be focusing on will be like flash lamp sintering of oxide ceramics again. But Professor Losego asked me also to focus on thermal temperature, like measurements of the sintering mechanism again. So they are trying to develop new approaches and also try to find like already existing approaches to measure the real temperature of the interaction. So that will be very interesting. I'm very happy that I'm not going far from, of course, this is like personally depend on everybody, but I'm happy to stay in the additive manufacturing of ceramics.
Okay. And for the future, do you have any?
For now, it's going to be 4 years, this postdoc position in Georgia Tech. And I think I will try to see which makes me happy, like staying in the US or coming back to Europe. But I'm right now like 50-50. I just want to experience what comes. That's also politically correct.
Yes, but it's not easy to answer this kind of question. Don't worry about that. Okay. I don't know if we have a question, but if not, it will be time to shift to the next presentation.
David, if I still have 1 minute.
Yeah.
Since this is the end of the project, and sometimes you were asking, what do you keep after all this project and your opinion and so on. Since this is the end, as I said, I would like to say that, of course, this project changed our lives in general. I don't know if these kind of European projects typically are as good as this was, to be honest, because for sure we were talking a lot about boosting our career. We can see some of us were in one of the best universities of material science and so on. We got a lot of results. We were involved in organization, even of ceramic conferences and so on, even we are still very young. But at the end, what you keep for sure after one of these projects is people. And in this term, if I will remember DOC-3D printing for something, will be because of the human people and team working there. As you know, for example, I was living with Pedro almost 3 years. Then I was living with Nicola and so on. So I would say the best part of this project, apart from the scientific part and so on, that is very important. Finally, you keep people with you. And I can say that we create some kind of family, we create friends. And I'm sure, for example, in the future, if I get married one day, some of you will come to my wedding and so on. So that means how important was this project for us. Yes, not because of our career, but because we create kind of family. And it was very nice, guys. And it's a pity this is the end.
Yeah. Thank you for that. But in fact, it's the end of the project, but it's a continuation of the network. And in fact, the name of this project is International Training Network. No? And in fact, it's what is at the end also. But thank you for this nice feedback. And it's true, I hope we will still keep in contact and discuss a lot, share and do many things, including going to the many events. Okay. This is time for the next presentation. And Ambra, Catherine.
Hi there.
Incotech. And if you want to share the screen, it would be very nice.
Yes. Okay, let's share this presentation. It's okay?
Perfect. The stage is yours.
Okay.
You can put on the full screen.
Yes, here I am.
Perfect.
So, hi everyone. I hope my connection will not fail. This is why I wasn't opening my camera, because it's a bit low. So you'll tell me if it starts bagging. I'll just turn off my camera. Well, I'll present you some of the work about my thesis that concern lithography-based ceramic manufacturing of semi-porous orthopedic implants. So from the printed parts to the tribology and the design of a whole finger joint prototype. So I worked in collaboration. I was in Lincotech Medical in Trento with Marzio Piccini, who was my first supervisor, along with Artemis Samulis from the University of Birmingham. And I did several secondments in lithos and especially at the IMP of Toulouse. Just a quick reminder of the project objectives. So basically, it was all around the investigation into these lithography-based ceramic parts for orthopedic application. And so the 4 steps that followed were certainly the evaluation of the printed materials in the first time in terms of surface finishing and microstructure. Then we insisted a lot on the tribological behavior of printed parts in air in the first time and in the fluid-like environment, because we wanted to represent the main joint application. And then we still wanted to produce semi-porous parts, as I said. So we focused on different porous lattice analysis for a comparison. And at the end, we get to put these 2 parts together to have a semi-porous finger implant prototype. So just to give you a little bit of the context, this is just a map I did for my thesis that grouped the 3 main state-of-the-art I had to face for the bibliography analysis for my thesis. So we have a big part concerning additive manufacturing. And I will not go into details now because I think we all have an idea of what this manufacturing of ceramics is at this point. And then there is also a big part concerning the choice of the materials. So I working on on joints in general, we needed materials that were performing in terms of tribology, as I said. So we selected advanced hard materials as alumina, stabilized or partially stabilized zirconia, and ZTA, zirconia total alumina. And both these fields together bring us to analyze the background of the arthroplasty implants from the general history to the finger joints that were the more focused subject of the thesis. So this is why I wanted to show you quickly, just to have an idea of the state of the art, the existing and implanted, and the history of finger joints. So there is a long history that is still ongoing of silicon implants. So it's a single part because it's an elastomer, it's a flexible material, so it's made of one part by casting, by simple molding manufacturing. But there are lots of problems of adhesion and failure of these implants, and this is why there was an advancement in the state of the art in the literature, and the research started focusing on 2 parts implants. So this is a composite metallic implant. So we have a metal part with a coating to improve the adhesion to the bone. Then we have new studies about with new materials as pyrocarbon and once again metal, cemented metal or coated metal with polyethylene parts. So these joints came out. I don't know if you see my. These joints came out after the boom of hip and knee implants. So obviously are the same material, but there is still an interest and a challenge in the field because even these more recent processes present problems in terms of adhesion, in terms of the fact that we still need to coat the implant to improve the adherence. We have very heavy materials, so hard to put in hands. So this is why we decided to focus on it with the additive manufacturing of ceramics for this application. Another map, it's the last one, I promise, just to give a general idea of all the experimental part of my thesis, because it's hard to get it in its totality, because there are very different subjects, from the design and the selection of lattice design and analysis, because I did it with in the first time with the modeling, and then I also printed porous lattices and experimentally tested them until the design of the semi-porous part. But in parallel, I also analyzed the tribology of the dense part. So all of this orange part concern the dense components. And in the last months of my PhD, I tried to put all of this together to do an implant prototype that presented both the lattice optimization and also the material and tribology best performance. So today I will just present you two very small outcomes, two very small results, just because I find that are maybe more uncommon or more interesting, completely unrelated between each other. So, but just to, I just thought that they were the most, maybe, I don't know, inspiring, interesting, could be useful. For the materials and methods, I worked on, as I said, on alumina and zirconia, so mainly ZTA and zirconia, both R&D and commercialized slurries by Litos, and the less recent Serafab 7500 printer that works with the DLP lithography, so digital light processing with the mask technology that you see here in the bottom-up approach. So you have the platform, and the samples are built from the internet. So the first result will concern the tribology test. I use the tribometer that could perform in air and in a liquid environment. As the liquid environment, we selected the bovine serum because it's very similar to the human serum, and it's very it's used for many in vivo-like tests, especially for tribology. We printed disc and ball geometries with the customized dimension and shape for specifically for this test, and with the reference to try to analyze always the same angle, and to have a reference also of the staircase effect that is typical of additive manufactured samples. And this is the result I want to show you today. It's a result that scared me the first time, because as you can see, you have the volume loss. I didn't show you the friction coefficient, but I just wanted to insist on the volume loss after the test. So basically, I performed the tribological test, and then I measured the volume loss by 3D scanning. And I find out something very strange, that in air, I had less volume loss than in the liquid environment, which is strange, because when we lubrify with a liquid, we are supposed to wear less. So we tried to understand this phenomenon, and we figured out that this was due to the fact that in the liquid environment, so the lubricated environment surface, we just had a sort of polishing effect. So here you have the surface before the tribology, and here you have the surface after. And basically, you can see that the surface is just polished. It's very visible here because we have this crack that show us the difference between the before here and the after test here. It's the same effect that we have after polishing. It was different in air condition because we could imagine and see a little bit as well a film on the surface that was covering the grain that were underneath this tribal film. And after several characterization, we figured out that we were right, that it was a tribal film, so a film that was formed during the test in air. And we saw it by cross-section SEM analysis. So you can see that we have, before the test, we don't have anything, and after test, we can see micrometric tribal film. We wanted to analyze this, and we found very different results for zirconia and alumina parts. So here we have stabilized zirconia Raman mapping to understand what was the composition and the phases of this tribal film. And you can see here that we have different phases from on the tribal film. We have we have the a change of phase, so the monoclinic phase of this zirconia that starts to appear. Just a quick reminder, I didn't put the zirconia phases, but the stabilized, partially stabilized zirconia is a tetragonal structure, and it's partially stabilized to avoid the to monoclinic zirconia, which is unstable and can lead to cracks due to the phase transition. So this is something we normally want to avoid, but with stress condition or humidity condition, it can still happen, and this is what happened during the test. And it's even more clear here because we can see that on the film we have an homogeneous phase of tetragonal zirconia, but underneath it, here in the sort of cracks that we have on the tribal film, we can see that under it we have monoclinic zirconia that is appearing. So this was also confirmed by other analyses as XPS and EM analysis. And on the other hand, the zirconia, the alumina tribal film was another transition, but in this case, this was due to the formation of aluminum hydroxide on the surface. And this was also confirmed by Raman mapping and the TM analysis. And yes, I will not go into details because it's a lot of technology of characterization in detail, but it's just to say that we figured out that the formation of a tribal film during air tribology tests can prevent the propagation of wear and limit the volume loss. So this can give an idea for post-treatment for alumina zirconia parts, for example, in order to improve their wear resistance, their tribological properties. And this is something we didn't see in a lubricated environment. So the second and last point I wanted to show concern the lattice, so the porous side of the parts, and we analyzed. We were linked to the software we were using, so SolidWorks, and the configuration we can obtain with this software. So we insisted on regular cubic unit cell lattices, and we have a simple cube, a center face cube, and a reinforced center face cube. Here we have an hexagonal unit cell. So these are the cubic ones. These are the other ones. So hexagonal, tilted cube, and randomized cube. And for the cubic unit cell, we decided to start with the first screening to reduce the printing, and we did it by modeling. So the modeling showed, we compared it with a dense reference as well, but we found out better properties for the simple cube. because in the case of centered unit cells, we had an accumulation of stress very high into the center of the unit cell. So we went on also with different analysis for the non-cubic unit cell and with the most performing cubic unit cell, so the A, the D, the A, and the F, and we printed these samples, and we performed real tests on these samples. And we figured out that actually the tilted simple cube, so this geometry, which is the same here, had significantly better performances, so a much higher breaking stress for the same porosity percentage. So basically, it was the winner lattice, let's say. And with this one, we also tried to compare other properties as the influence of the printing orientation. So we simply printed the same lattice with the grid oriented in a different way, and we obtained the same properties, meaning that the printing didn't really influence the mechanical properties, which was a very good result, because this means that we have a very good adherence between the layers. And we also evaluated the influence of the geometry orientation. So in this case, it was more an analysis of the anisotropy, the isotropy or the anisotropy of this particular lattice. And in this case, unfortunately, but it was expected, we had a much lower breaking stress in the case of the test direction perpendicularly to the grid. So we had this sort of planes that were accumulation of charge and were preferential rupture planes. So the conclusion concerning this small part of results was that we didn't have a printing influence of the printing orientation on the structure, meaning a good adhesion, as I said, and a good printing performance in general. And on the other hand, the anisotropy is something that we must consider when we are gonna design our prototype and our lattice on its prototype, because we will need to consider which direction we have to prioritize in terms of best mechanical performance. I think that's it. This is just the list of the conferences. Posters, mainly our presentation posters is both online and presence. And the awards, and we wrote a publication on open ceramics in 2021. And also the list of the secondments, since there were a lot of it during my PhD. I thought it was worth mentioning, especially because of the great support I had from the EMP of Toulouse and from Litus for the printing parts and for Linkotech all along, and the University of Birmingham from an academic point of view. And obviously, thank you all, especially David Dion for the organization and for all the beautiful things that Alejandro already told and I share completely. And if you have questions, I'm here for that.
Thank you for your nice presentation. It's open for question. If you
I have a question, if I can, Ambra.
Of course.
Hi. So for the design of the samples, the geometries, did you use any modelization models like to optimize the, to check with the bone growth and stuff?
Yeah, this is a very good point, because actually, unfortunately, all of the geometries I tried are mainly cubic pores, and there are lots of tests that prioritize, as also Islam said, and as it's now well known, the rounded pores are much better for the cell vascularization and for the cell ingrowth. Unfortunately, I wasn't well equipped for the design of such a complex, let's say, lattices, because the majority of these I designed it myself. So this, for example, I had the SolidWorks training, and for example, the cubic grid, I designed myself all the pores, you know, like it's not optimized at all. And for the other, for example, the hexagonal and randomized, we had medical lattice, something like that. It's a software that helps you perform the design, but you're limited to the design that the software offers you. And this is why I insisted on this. But if I could go back and I don't know, try something else, I would insist on trying more rounded shapes for the pore and for the lattice to favorize the vascularization and the bone adherence, because
Have you seen some studies that are using like models to optimize like a design in the literature? I mean,
yes,
yeah, okay.
I actually did, not for my thesis, actually, for a new project I was working on. I did a lot of state of art on this, and this is what made me think, why did I do that? I mean, obviously, there is also the other side of the coin, let's say, because when you have cubic pore and cubic unique cells like this, you have poorer biology properties and cell adhesion, but you have increased mechanical properties.
Okay.
So if we want to focus on it depends on what you want to prioritize. There's always something that is in lack. Because you prioritize the biology and you have worse mechanical properties.
It's a compromise. Okay.
Yeah, exactly.
Thank you.
Thank you.
I do have a little question, but I think Islam also has one. Go ahead.
Just a small question. I remember that in 2020 you was working also on a kind of structure that is similar to the bone structure.
It's the gyroid, I think.
No, it wasn't the gyroid. It was a complex structure that you found, I think, that you presented to us.
Really?
Yeah.
It could be. It was the trabecular. Yes, it was the trabecular, right?
Yeah. I think
Yes.
so. But
this is a good point, because this is another very complex structure that was offered by the lattice software I was using. So I was able to design it. The problem is that this structure wasn't printable by SLA bottom-up approach, because we had too many hanging out points, and you are a bit limited in this kind of structure with SLA, because especially not with SLA in general, but with the bottom-up approach, because it's very hard to explain without a table. But basically, if you have one layer that is not supported by the surrounding one, you are just creating one small part alone into your vat, and the following one will be blocked by this that is stacked on the bottom of the vat and not on your sample. I don't know if I'm clear.
Yeah, I understand very well.
Okay,
and
perfect.
Are the pore in this kind of structure interconnected? So can we clean this kind of pore, in your opinion?
Yes, it's actually designed for that. And this software that is called Lattice Medical or something like that is specifically made for medical lattice. So all the geometry they propose present interconnected porosity.
Okay.
Because it's done on purpose for this kind of applications.
Can you send me one of this lattice? I just want to try to print it and to see if
yes, of course, with pleasure. I think I should be able to find it in some stock.
Thank you, Amber.
You're welcome.
It's your time, Aaron, for the question.
Yeah, I was actually gonna ask something very parallel to Islam, and also, you think those companies that you are working, Linkoteng and Litos, they are planning to bring this project to like another level, or they just like fine with the results? And
are there any? No, I don't think so. I mean, I completely changed the project, but we did a prototype, a design and everything, but the PI is the IP in English is
okay.
on Linkotech, and I don't think for the moment they are going on.
Maybe we can ask to Marzio and Martin because they are connected. So I don't know if they want to reply.
Or if they want to just explain how they work in this project on a few words about Umbra, but I don't know if they are.
Yes.
Yes.
Yes. Thanks. Thanks, Angra, for your collaboration with Linkotech. It was very appreciated your work. Unfortunately, this project was very nice for us, but not enough. In sense that the company is produce many devices with other technologies, not just stereolithography, but they're using other laser machines for making devices. For unfortunately, at this time, the target is to improve this technology, but of course, we are looking for other techniques, other machines. So I'm very, let's say, not so happy about it, because of course we know how was important this project and how many results gave us this project, and I try to insist to convince the company to work on it, but they say me that they want to invest in other projects right now. But of course, this work was very appreciated in our company, and so I would like to thanks to all of you for this opportunity. Of course, it's something that new for us, and so thanks to all students and professors and other guys that work on it.
Thank you, Marzio, for that. I think, Martin, you are here. If you want
yes, I'm also here, but the camera. No.
Yes, thank you.
Yeah, also from my side, thanks to Ambra. It was a very pleasant and interesting collaboration, and a very nice wrap up today. Yeah, we are basically also waiting for Linkotech, hopefully to pull the trigger on this at some point. Of course, we perfectly understand also the company's position that it takes time until you can move forward with some project results. But it was quite promising, and I think for us it was also very helpful. Also the findings, especially with those whole lattice designs, and this will be transferable to other applications. So this is certainly no stuff that's gonna gather dust in a drawer. So we are continuing to work on that, not for the particular application of Ambra's project, but for other applications. So it was very interesting for us, and also thanks again for everybody who was involved in this very fruitful collaboration.
Thank you, Martin. And maybe I have still a question for you. Maybe if you want to just explain to other company what is the main advantage to be involved in this kind of European project? If you want to say a few words about that.
I mean, if you're lucky and you get a really good student who works on your topic, then this is can be a big benefit, because you have somebody who can take charge of a certain project, really focus on it. Maybe also topics that are not directly in the focus of your daily business. So this is one of the advantages, and of course also the network that this project offers you. So Ambra has shown a lot of very nice results from rather fancy characterization techniques that especially a smaller company does not have access to. And such a project can be a very nice vehicle to also get access to infrastructure, to know-how, expertise that you don't have, that you have internally. So those were for us the main, the main motivation, and it really also paid off in this respect, that we could really learn also quite a bit, especially when it came to these tribological properties, or also the printing of definitely something that we would do again if it comes to the decision.
Okay, thank you for this nice answer, Martin. Ambra, we have also the same question for the other student. What are you doing now, and what is your future?
I don't know what's my future.
Yeah.
But my present is being a project manager into a startup that in January actually will not be a startup anymore, because we are growing quite fast, and I'm happy about it. They patented a new additive manufacturing process, which is called dynamic molding, and basically they were printing silicon. And I was very lost when I arrived, because I don't know silicon at all. But they hired me to work on the printing of ceramics with this technology, and to work on any new possible materials. So I'm also working on composite, on metals, and it's amazing, honestly, to have this possibility onto this wide range of responsibilities, of projects of different natures, to still work on additive manufacturing of ceramics for the medical field, but at the same time also working for aeronautic projects, for big companies and small companies, collaboration and customers. I'm happy.
Perfect. It's very nice. Sorry, but we will need to change to the next speaker, because we are a little bit late now. And my pleasure. Thank you again, Ambra. But it's my pleasure to introduce Professor Ion Miliescu from the NFLPR in Romania, and which are in charge of the work package 5. Ion, if you want to speak.
Yes, I'm here. Hello, de Magurele. Bonjour à tous. Well, this work package, modeling and characterization, it has 2 main subchapters. One is about materials modeling, and the second is on process modeling. They were run by 2 our students. First, Mohamed Arif Mahmoud was running his thesis and his work here in Magurele with me. And the second, Mohamed Ali Asaf Cherry, who ran his work in Birmingham under the leadership of Artemis Sambunis. So there are plenty of results in this, my opinion, this spec. I made the reports, can be run if you want to go to it. And I would like to leave some more time to my students, the 2 students, one is mine, second is Artemis, present directly the work they done. But I will start by two, let's say, reflection points. First is that everything demonstrated finally that good modeling saves a lot of work, a lot of experiments, a lot of money, a lot of time. So having a good model can help with everything. And second is that in time, in not very long time, in 3 years, a lot of valuable results have been obtained, exceptional results, in my opinion, which can be reported to the benefit of these contracts. Well, there were 27 published papers in reputed ICI journals. There were 10 oral presentations and post-presentation to international conferences, and several international awards. And finally, one point, which is not at all usual, as you see. So a lot of different models have been used for modeling. Let's say heat equation, Fourier and non-Fourier approach, integral transform, fractal theory, and also a very unusual artificial neural algorithm for the first time. And this last paper, which was published in 2021, we are now in 2022, had in 1 year 29 citations. It never happened in my long experience as author, as the editor, as member of the board, that the paper accumulates in a year 29 citations, independent citations. It is usually, they explode in the second or third year. So we are going to expect from here a big development, in my opinion. And now I would like to pass the word first to Arif, and then to Mohammad Ali to give you all details of their work. Arif, can you hear me? Arif?
Yes,
Arif
Professor.
Okay, Arif is now in United States, in Missouri. He finished his thesis very fast, plenty of work and results. He got summa cum laude as a qualification. David was for the thesis in Bucharest. And after that, he passed 1 year at the Texas University, Qatar, and now he is in Missouri for working in digital development, digital factory development, including a lot of developments for future 3D installations. So please, Alice, proceed.
Professor David, can you please allow me to share my screen?
Yes, yes, you can go.
Yeah.
Thank you, Arif. We here?
So can you see my screen?
Yes, but could you put in the full screen? Perfect. You might need to duplicate or swap.
Perfect.
Perfect. The stage is
Hello.
yours.
Yeah, sure. Thank you. Hello and good day to everyone. My name is Mohammad Arif Mahmood. I worked as an ESR 13 at National Institute for Laser, Plasma and Radiation Physics, Romania, under the title Characterization and Modeling of Optical Properties and Dispersing of Ceramic Materials. So during my PhD studies, I worked on two types of laser-based additive manufacturing systems. The first one is the powder-based system, what we also call it laser powder bed fusion, and the direct energy deposition system. So both systems are completely different from each other. In the first one, we usually have a layer of a powder bed, and which is selectively belted by the highly focused laser beam, while in the DED process, we involve the coaxial addition of the powder or the wire, which is melted by the laser beam and deposited in our desired path. So during these studies, we developed several simulation models, such as on the dimensions of the deposited layer for the residual stresses distribution, average microstructure formation, and powder flow simulation. So let me first begin from the residual stresses and the deposited layer dimensions. So what we did here in this model, we developed a model to estimate the dimensions for the single layer. Then we introduced the hatch distance to calculate the remelting depth so that we can estimate the dimensions for all the deposited layers. And following on, we use these dimensions in my stresses and strain distribution model so that we can estimate and predict stresses within the deposited layer and the substrate. And we compared our results with the experimental analysis, and we compared a very close correlations compared to the experimental ones. So the advantage of the analytical models here is that they are computationally efficient compared to CFD simulations or FEM based simulations. So in the next study, we developed a simulation model for the powder stream in the DED process and the thermal analysis. So this is a typical diagram for a 3-beam nozzle powder nozzle. So it usually involves the 3 subnozzles, and the powder is entered in this direction, and interaction at this point, which is known as the point A, takes place. And here it usually adopts a Gaussian shape, which we actually captured using the high-speed imaging camera at INF-LPR. And for this one, we developed a simulation model which was able to predict the profile of the powder. And following on, we compared our results with the experimental ones, and we found a close correlation between the studies. And then we developed a sensitivity analysis, means we changed the process parameters, and we identified that in the DED, there are 3 types of powder shapes available. The first one is the Gaussian one, the second one is the transition one, and the third one is the annular stream. Then we developed a simulation model to predict the average grain size and the corresponding mechanical properties. So what we did here, we developed the model for the thermal history in the deposited layer. Then we used this thermal history to calculate the thermal stresses and strain. Then following on, we introduced these dimensions in our JMAC model so that we can estimate the average grain size. So this average grain size was used to calculate the mechanical properties such as ultimate tensile strength, yield strength, and the hardness. So we were only able to perform hardness testing using an indenter, which is the Vickers hardness tester, because the dimension of the layers were very small and we cannot perform the other analysis. So we validated our results, and we can see a close correlation between the experimental analysis and the theoretical ones. Following on, I did my secondment at Ermaxon Innovative Technologies on the laser powder bed fusion. And here we printed some samples for the COCR alloy and performed some non-destructive analysis using X-ray computed tomography. So in my point of view, X-ray computed tomography is one of the unique tools which will help you to identify the pores and the defects, the size of the defects, their shape, and their distribution within the printed sample. So based on the dimensions of the sample, you can identify whether it is a defect of lack of fusion or the keyhole based porosity, or the porosity due to the cracks. And we also tried to characterize the average grain size based on the operating conditions. Then following on, we did the collaboration with the Ermaxon Innovative Technologies with Asifur Rahman, and we developed some simulations for the DED process. And in these simulations, we highlighted 2 novel phenomena. The first one is the splashing of the melt pool and the powder particles in the DED process, and the back and the forth movement of the melt pool. And then we also developed an analytical model so that we can compare our results, CFD results, and the experimental ones with the analytical solutions. Following on, we converted the single layer deposition into a contour based. So it was not a straight line, it was a square. And we highlighted here that the contours in the DED process, they are taking a lot of time to solidify compared to the straight line. This is because here at the contours, the DED robot actually tries to adjust its speed, and on the contours, it is usually slower compared to the straight lines. And here the melt pool enters in the keyhole mode compared to the conduction mode, which is causing a lot of time to solidify, and a lot of defects were identified at the contours. And again, we compared our results with the experimental analysis and identified a close correspondence between the two. Then we carried out the printing of aluminum, silicon, tin, magnesium alloy in collaboration with the Ermaksan Innovative Technologies, Asif Rahman. And we tried to optimize the process parameters based on the visual inspections. And we can see here that the sample 15 was able to give the very least defects compared to the other samples. Then following on, we carried out the simulations for the keyhole formation in the laser powder bed fission of titanium alloy. Besides, we developed an analytical model. So we can see here that these results on the right-hand side were predicted by the CFD model Flow 3D software, while on the left-hand side, the keyhole dimensions were predicted by the analytical model. So the shape is quite close to each other. Then for the DED process, we tried to optimize the process parameters, means we didn't use any post-processing technique, and we tried to optimize the parameters so that we can eliminate defects or at least reduce it to some extent. So we can see here that based on the parameters optimization, we were able to reduce defects up to 99%. Then following on, we also worked on the process automation. So here what we did, we developed an analytical model for the keyhole formation in the DED process. We validated our model with the experimental ones, and then we linked it with the neural network. So this will lead us to the process automation, so that in the near future, if I want to identify the effect of the parameters on the keyhole formation, so we just need to give the inputs, the model will be able to give output instantly. Then moving on from the metals to ceramics, we developed the simulation model for the laser additive manufacturing of the bulk substrate and the powder bed. So here we validated our model with the silicon nitride bulk substrate and the laser to alumina powder bed interaction. And here we can see that the thermal distribution across the substrate and the powder bed. And again, we validated our results with the experimental analysis. So in conclusions, we developed several efficient models for the thermal distribution, microstructure evolution, mechanical properties, porosity in the case of laser additive manufacturing processes. Then we compared our results with the experimental ones, and the results were within the range of 4 to 15% accuracy. We performed the experimentation for the stainless steel and the titanium alloy. Then we also implemented the X-ray computed tomography on the titanium alloy. And besides, we developed the simulation models for the laser additive manufacturing of bulk and powder particles. So in this study, we developed the time and cost-effective techniques that can be used further for the process optimization and the estimation. So the list of the contributions, like during my stay at INFLPR and Ermaksan, we published lots of papers with a cumulative ISI factor of 41.575 and the AIS factor 6.33. Besides, we participated in the international conferences such as ASTM conference in the United States and the national conference in Romania. And I did my secondment at Ermaksan as well, where I worked on the COCR alloy. We performed experiments. We performed the samples for the tensile testing. We also prepared the end product for the medical applications, and we characterized them using SEM, XRD, tensile tester, and X-ray computed tomography. So thank you so much. So currently now I'm working at Missouri University of Science and Technology, and here we are implementing a concept of Industry 4.0. So the concept is like we will be developing a digital factory. So it will be like involving all the departments such as electrical, mechanical, and computer science, and we will develop this factory for the industrial use. Thank you so much.
Thank you for your very nice presentation, Arif. I don't know if someone wants to ask a few questions, but I have a lot of questions. But maybe I will start by the end. You speak about the industry 4.0.
Yeah.
And just what could be the 3.0 and 2.0? Because I still don't know, in fact.
So there were different revolutions. So for industry 4.0, we usually involve like additive manufacturing, IoT, machine learning, and simulation and the modeling, all these techniques. So what we usually do, we just send the part directly. So for example, if you want to print a part, so you will just send it to us. We will print everything. There is no need for the human to machine interaction. So everything will be performed by the robot.
Mm-hmm. Okay, it's a little bit more clear. Thank you very much for that, because I'm not really involved in that, but thank you for that. I don't know if we still have a question from the room. If not, I still have a question, in fact. You wrote a lot of paper, and I would like to ask to you if you have some...
David,
yes,
just a point.
Yes.
I want to say he came in Bucharest on 7th of June 2019 and left us in February 22. So all this work was done in 2 years almost.
Yes.
Okay. I would, me personally, it helps that Arif does not here now, I would have liked that he remains somewhere in Europe.
Okay. Thank you for your comment. Yes, it's a very short time for PhD. It's true. And I will back to my questions about the article, because you wrote many articles, and if you want to give some informations to the future PhD student in European project to increase the number of papers, do you have some secret, or do you have some things to
magic?
Or
No, actually, Professor, like first of all, for the analytical simulations, if you will write or publish anything, it will be novel. And the second thing is, for the research point of view, you have this research should be question based. It's not like we are just doing everything and we don't know what we are doing. So it's very important. So this will ultimately increase the number of papers, means your approach. So if you have question based research, I think it's very simple.
Okay.
I have one question. Can you use the same machine learning robot to write the articles or not?
Maybe wrong.
Not answer.
That's machine.
Yeah. I know, Arif, you are very also focused on perform modeling, but also validate that by experimentation.
Yeah.
And is it so easy to do some validation of modeling, in fact, or?
So, Professor, there are two approaches which are generally used. The first is like, do you experiment by yourself, or perform, take the data from literature with the references, of course, and permission. So in my case, we have used the both techniques. We performed the experiments as well. We took the data from the literature, but of course with the permission.
Okay.
Yeah.
Okay. And if you have some remarks for people which could help you to reuse the data performed by other scientific, do you have some suggestion for to make it easy for people which perform simulation, or what is the ideal way to present the data for a very nice reuse?
Yeah, Professor, means they can use, or if they are not able to identify the approach, they can contact me easily.
Okay, okay. You will do the job and do the simulation.
David, I have a question. Arif, you work only on metallic alloy, no on ceramics?
No, we worked on the modeling of the ceramics as well. Like as I showed, let me.
Yeah, it start to develop modeling and metal and then shift to ceramics after.
Yeah.
Okay. Because perhaps it's easier to find data in metals than for ceramics, no?
Yeah.
It's pretty difficult because there are only a few. Because for the modeling we need some properties like thermophysical properties, including density, specific heat, and all those stuff. And in the case of powder, because the properties for the bulk material is different compared to the one which we are using for the powder bed. So we can never apply properties on the both cases.
Yeah.
So this was pretty difficult, but not impossible. So there are a few people, I don't know the name, I think Shri Ram or someone who's working on the laser additive manufacturing of ceramic materials. So we took the data from that guy.
Okay. And the last comment, Arif, I think I didn't receive your career plan, the last one.
Yeah, actually I received your email, but the thing was like I was pretty busy.
Okay.
Previously. So before coming to US, I was working at Texas A&M University at Qatar as a postdoc. So there were lots of responsibilities for me, like research, teaching, and guiding students. So I was not able to find time. Besides, I recently got married, so that was another issue.
Congratulations.
Yes, but you think to send me it in the next in the following weeks, I hope.
Yeah, I will send it.
Arif is always running, you see. He never sleeps.
Yeah. Okay, thank you.
And
thank you so much.
And what is your future, Arif? Do you have a? Do you know what you want to do after? Yeah?
You have not a permanent position in Missouri, or?
Probably soon, not now.
Mm.
Yeah. No, actually, previously I was offered a permanent position.
Okay.
Yeah, in Poland, but I didn't want to go there, so I decided to come here. Yeah.
Okay.
At AGH University, it was the mechatronics department, so they were working on some classical theories.
And you want to work in a university?
Yes, I want to work in a university and probably as a professor.
I think it could be nice.
Thank you so much.
I think we will be late. I don't know if we still have the time for one question, but if not, we will shift to the other one. I think it's time to congratulate Arif and to shift to the other speaker. I think is here. It's Mohammed.
Yes, I am here.
Do you want to share your screen?
Just a second, please.
Yeah.
Okay, can you see my screen now?
Yes. Nicely.
Okay. So my name is Mohammed Ali, and I was ESR 14 for DOC-3D printing project under Professor Artemis Stambulis and Dr. William David Griffiths. So today I'm going to talk about numerical modeling of additive manufacturing, to be specific, selective laser sintering process that we developed codes for. So in our project, we developed codes for numerical models that covered powder delivery, laser irradiation, and sintering and selective laser sintering limited scale process. Usually we used mainly C++ for development of our libraries, and for subroutines for FEM we use Fortran. And we employed Altair EDEM solver for DEM simulation, Abacus CAE for FEM simulations, and in parallel we developed C++ libraries and Fortran subroutines. For like powder delivery, we used DEM, Altair DEM, and for roughness evaluations for the powder beds, we developed a ray tracing method in C++. For irradiation and laser scanning model, we use FEM and also ray tracing with DEM. And for free sintering heat-based powders fusion models, we use C++ again. So starting with powder delivery and layer formation simulations. So this work was actually done in collaboration with Belgium Ceramic Research Center. The idea was that we use different mixture of powders of different size distributions from fine to coarse, and studied the blade-based delivery and subsequent packing densities and surface roughness. So in our DEM simulations, we first generated the correct volumetric distributions of powder as close as possible, since the powder particles are randomly generated within the given parametric confines. 100% match is not possible with the experimental one. Like the red bar represents the experimental data that was provided by BCRC, and the blue one is the one that we generated. So after setting up certain parameters, we kept on generating the data for like 4 or 5 times to make sure that each time the distribution always ends up as close as possible to the experimental powders. So in the input parameters for software include mean size, standard deviation, and upper and lower caps of the powder size. So here you can have a look at one of the powder samples, which compares DEM generation on the left-hand side and actual optical laser image of the actual powders, which you can see is quite close to each other. And calibration of and then this is the important part, the calibration of the powders in DEM. This is to make sure that DEM powders particles dynamically behave as close as possible to the actual powders. So one of the commonly utilized methods is static angle of repose, which we adopted. On the left-hand side, these are one of the sample of our simulation. And on the right-hand side, this is the actual powder at BCRC. So as I earlier discussed, that we had used different mixtures. So we had mainly 2 powders, so-called SP1 and SP2. SP1 was the finer powder and SP5 was the coarsest powder. We used different mixtures to obtain new distributions and then calibrated each of them. You can observe that as we move towards the coarser spectrum, the angle of repose becomes smaller. SP5 represents SP5 represents the coarser powder. SP1 represents the finer powders. So the coarser powders, this actually happens for a very good reason, that the coarser powders generally means that they contain larger particles having this within the same mass or quantity. But because of large size powder, we have smaller surface contact area compared to the finer powders, because finer powders are broken down even for the same mass, and they have larger resistance. That's why their angle of repose ends up quite bad actually compared to the coarser ones. So in this slide, you can see one of the sample videos for powder generation and layer formation process. The powder particles are deposited on top and then smoothed out by the blade. And please note that that the blade, the scraper that you used by BCRC had a round profile. So this is, which may look like a roller, but this is actually not a roller. This is simple blade with a circular profile on the tip. Here's one of the observations, that for our parameters that we observed that the first layer visually generated significant voids. Actually, this was, to be more specific, we used 3 different thicknesses. This was specifically for 100 micron thickness. 150 and 200 were actually better compared to this one, but this is the idea that to look into that. As we move toward the coarser part of the powders, they become visually even more, their first layer becomes even, you can observe visually significant voids on the coarser layers compared to the finer ones. So next was the powder surface roughness evaluation technique in DEM. We developed a ray tracing method for this. The idea behind it was to generate a discrete set of rays and shoot them towards the powder surface. So we start by taking a visual square domain some distance from the top surface of the powder, discretize them into the smaller cells, and allocate rays starting position in center of each one of them. So this is the side view. Actually, these rays are just virtual. And here you can see the rays falling down on the powder. Each ray would be eliminated at the point where it intersects the first powder particle, and its total travel would be recorded. In figure B, you can see the illustration of remaining rays of varying lengths. This is what we obtain at the end. So to quantify the surface roughness, we used parameter RA, so RA basically represents average deviation of lengths from the mean, and not to be confused with standard deviation. So this was our observation that variation in the finer powders tended to generate a smoother surface compared to the coarser ones, and these are our simulation results compared to the experimental results, which actually represented a quite close correlation. So next we will discuss the laser irradiation models that using a finite element method. So we used FEM-based software Abacus CE solver to simulate the laser scan on the powder bed surface in Fortran. We developed subroutines for definitions of laser heat flux and phase change on the element nodes, and the laser was defined using the Gaussian distribution equation given here. So here you can see a typical temperature distribution in the FEM from the lasers. In reality, as the result of powder beds, even uneven surfaces from morphology of particles, the laser light scattering would be affected. But in FEM, we are unable to do that because the FEM solver generally assumes this whole bed to be a continuum material rather than a powder particle. So we are unable, unfortunately, the light scattering is not possible to depict with this method. And the second downside of this method that we cannot observe the discrete sintering at micro scale as well. So to answer to the downside of that FEM, we developed another ray tracing method capable of identifying reflections, transmissions, and total external reflections based on Snell's law. So idea was similar to what we did for surface roughness evaluation. So we define a square of sides. We define a square which is equal to which has sides equal to the diameter of the laser beam, and then we discretize them into smaller cells and eliminate, and then allot the rays to each of the cells, and then eliminate all the rays that are out of the bounds of this of the laser beam actually. So all the rays are actually formed within this circle only. Then we allocate energy to each cell by Gaussian distribution. So the idea is again similar to what we did in FEM. Energy in the inner cells is highest, and outer cell tends to be lowest, and outside this circular bound is generally, we set the energy to 0 then. So this is just a repeat figure from FEM, just to show the comparison with the next one. So we used, for the similar set of parameters, we observe that with ray tracing method, we are able to see the effect of laser rays scattering outside the laser scan region as well. So you can see that, so this is actually a uniform particle size distribution. And you can observe a wider temperature field, even the laser scan region remains the same. So in this case, we have similar packing density, but non-uniform particle sizes. Again, a wider, this ray tracing method, our method can actually identify different particle sizes, no matter what, they don't have to be uniform. So we can have any kind of packing densities and anything. And our code will be able to evaluate where the rays actually strike and how they get reflected and how they actually interact with each of the rays, how it interacts with all of the particles. Even you can observe that on left and right side, you can observe that even the particles that have not been scanned, they start to gain energy because of these reflections from the rays, from the laser rays. And so in the last thing that we developed, which was this library was also developed in C++. The idea was that the EM particles that reach above a certain temperature for sintering, they would start to fuse together. This development was mainly based on works of Woburn, making Fermi and Coble actually. And so we defined the two components of sintering force between the particles, the normal component and the tangential component. And the normal component further consists of a centering or a driving force and a viscous force, which keeps the particle velocities in check by acting as a damper. Because when we are implementing this model, the most important thing is that we don't want any abrupt accelerations between the particles, because they can cause numerical instability, and you will observe that the particles goes kind of in an explosive trajectory. So we have to make sure that each of the particles from very beginning, they are in a quasi-static state. So for example, when these two particles are in contact and their temperature are raised above the centering temperature, so you have to actually estimate or set centering temperature and then incorporate into your code actually. So and then in the figure B, you can observe they start to fuse together when the particle reaches above the centering temperature. So the most difficult and challenging part of the development after development of the code was numerical stability and attaining quasi-static state for large number of particles like here. The specific parameters and results will be in my thesis, which has to submit in due course. So this is just an independent sintering model. This is just a sample implementation of our code that we developed. So then we brought this code forward. In this example, you can see the top surface of the powder bed and this certain highlighted region, which is subjected to a laser scan actually. That is causes the particles to gain the temperature using the ray tracing method. So now we are using actually two models, and we are incorporating with DEM now. So you can see in the enlarged portion in the gray figure that the particles are in contact, but they are not just fused together. So this is the after effect of laser scan. The particles start to fuse together using sintering equations and models and the library that we developed. And here you can see how particles within this video, within the scan region, start to center and densify. And as a conclusive remark, the codes that we developed are actually transferable to open source with some redevelopment required, but we do plan to release open source in future, so they are actually more accessible to 3D printing research community. In this way, researchers on limited funds should not have to invest in very expensive commercial solvers, and they will be able to work on improving and changing them, or maybe even adopting them for any other purpose. So these codes. So here's a closer look at centering and densifying and a numerically stable solution that we obtained at the end. So thank you. These are the references. And so the plan dissemination is first of all is my PhD thesis, which I'm working at the moment and actually close to completion right now. And we have actually two manuscripts, one review paper in collaboration with Armaksan, and one paper that we are independently have written, which we are going to submit in due course, and another planned manuscripts on powder delivery systems with the work on which we did in collaboration with Belgian Ceramic Research Center. Thank you everyone for listening.
Thank you for this nice presentation. It's time for question. Don't be shy. Okay, maybe I will start.
Yes, I have a question, David. Ali, where do you perform your second month? You went to Mons, to BCRC?
No, actually, I could not perform any secondment, unfortunately, because of COVID and then some other visa issues after that we had.
Okay,
so
okay.
All the work that we had done in collaboration was actually a kind of online, and they provided us the results and parameter exchange.
Okay, this Kirong sent you the different spray dry powder, is that?
Yes, it's the same powder that we use for analysis in our DEM. It's an alumina powder actually.
Okay, yeah, yes.
I've actually not included a lot of details here because of this public event, but everything is going to be in my thesis very specifically.
Okay. And the second question is, you are writing your PhD thesis is already written and you have already defend.
No, I have to defend it before March actually. So most probably I'm going to submit before end of January. That's what I'm planning right now. So it's almost in the end. It's with the I've already given most of the chapters for review.
Okay.
To Artemis, yeah.
And you have presented your result in international conference. I didn't see.
Actually, I only presented in one of the conferences. Actually, Artemis has to do it on my behalf because of, again, visa issues that I have been facing throughout.
Okay, thank you.
I have a comment, if you permit that. So you asked about secondment. No, nor him, neither Arif could do the secondment because they had been refused the visa. Arif, well, tried 3 times to go to France, to Portugal, either refused, definitely. In America now, he got the visa in 2 weeks.
Yes.
For work.
Yes. It's sometimes complicated.
What can you think about? Is the security in America at a lower level than here? I don't think.
But yes, it's very strange. Yes.
Yeah, it's very strange. It's a very critical point for this project because we have many countries which are not in a Schengen area, and it was very surprising for me and also many people to see the number of rejection of the visa or visa which are too late, and it's very ashamed for that. And for sure, we will send some remark, some feedback about this project, and we will write that because it's a very, very bad point. And but we was a little bit lucky because during the COVID, many conference was a hybrid, but if not, it could be a nightmare. In fact, it's a very important, but we never successfully meet together.
Yeah, with all the
PhD.
Because Arif could not travel, and yeah, it wasn't possible to meet all together.
This is very, very sad. But I don't know if you want to add something about this point, or maybe some PhD if they want to speak about that. But if not, I have also.
Yeah, Professor, I just have a comment. Like
Yeah.
on the other hand, it was good for me as well, because originally I was not planning to travel to Turkey, but I traveled there and we had a very successful collaboration with their Maxen.
Okay.
Yeah.
Nice point. At least. And I might have still a question about your research.
Yes.
Is it about you perform modeling of many parts of the printing, and do you want to what is the next step for modeling?
Actually, that as you can see that our models were actually quite original. We did not rely too much on any commercial software or anything. We developed our own libraries and then implemented them with one of the solvers. So the idea is that we should be able to transfer our models so they are available in open source for any researcher who wants to work on them. So like for now, sometimes we have to invest in expensive software like Flow3D or even EDEM, and their licenses cost thousands and thousands of euros or pounds per year. And that's what I don't want. I mean, the researchers should be able to have easy access, especially in 3D printing and additive manufacturing community for modeling and simulations. So that's what eventually I would like to do. And that's that was my first step, that I should develop my own models rather than relying on some companies' models. So I can easily share them with the wider community.
I have another question which are related.
Just a small comment. I think that this section, modeling, we can close with a conclusion. Modeling is the cheapest instrument. Costs less than any experiment. It saves money and time. For good modeling. So we should go always in parallel with experiments and a good model to understand what to do. This can save time and money a lot.
Yes, for sure. I have one question, Mohamed. It's do you have some strategy in mind for sharing open data on open modeling?
Actually, I do have it, because right now our models that were developed with help of EDEM's application programming interface. But right now, because these models are of our own, we have few open source codes in mind, like Mercury DPM. We would like to rewrite our codes and transfer them over there. It should not be a big task right now, because we have everything ready. Just we have to adopt to their syntax and formats. This can be a few months of task, but we can eventually get it done. This is what I'm planning right now.
Okay.
But there might be a little bit of, sorry.
Okay, and you will create some website for that, for the diffusion of the model, or what?
I haven't really thought of that. We can perhaps discuss this.
Okay.
How to, disseminate and bring this. I think website would be one of the good ideas.
Okay. And for about dissemination, did you maybe you want to go to specific congress or meet community which work on modeling, on open modeling or something like that? Is it existing? I still don't know.
Actually, there is one hosted in Austria. I'll have to check a date. When is their next one coming up? It's held by a company called Aspherix. It's a closed source software company, but they also do conferences on discrete element methods, and so maybe that would be one of the platforms to discuss these models and present them.
Okay. And I still have one question. It's more, what are you doing now, and what is your future? Okay.
Actually, recently I've started to work on another project with Artemis. It's on surface transfer of pathogens. So my work is again on numerical modeling of antimicrobial peptides. So we have to use the molecular dynamics and machine learning methods to develop new peptides and their interaction with different surfaces. So this is the idea. And in parallel, I'm of course completing this PhD thesis for DOC-3D printing. So right now I have two main tasks that are going on in parallel.
Okay. Okay, thank you for this nice presentation and nice answer. I think we finished with all the PhD students, but it's not finished for the final event because we still have some presentation of the work package 6, 7, and 8. And it's my pleasure to introduce Anne Lorich, which are from University Hauts-de-France, no, Polytechnique Hauts-de-France. And she's in charge of the work package 6 training. Do you want to share your screen, Anne, or?
I tried to share, but you didn't. It's not good.
No, it's okay.
Yeah, it's okay.
You can just put on the full screen and it's okay.
Yes, in the full. What? Comment est-ce que ça va? Comment est-ce que je fais ça?
Tout en bas, il y a un petit, juste à côté de la barre de.
Yes, yes.
Perfect.
Sorry, I have frog in my. How do you say? In French, we say a cat, but I have frog in my mouth. You know the expression in English? No? You hear me?
Yes, we hear you, but
Okay.
we still don't know what is the correct.
In Italian, it works.
How do you say?
In Italian, it works, the expression.
Yes, okay. Oh, yes, this. Okay, to remind the objective of the training work package, that was to give you the opportunity to complete your knowledge and expertise in the field of additive manufacturing. And also on the method to characterize the object. To improve your ability of analyzing, resolving problem, and so on to work in a multidisciplinary team. To create highly skilled researchers, but I think that today we have the proof that we succeed in the area of additive manufacturing. To encourage the mobility, we know that there were some problems with the visa. To create an active lifelong network of ESR, and then to assist you in formulating your project for the future. So the action to obtain this objective, that was we organized an induction school that was in Birmingham. You are coming, all of you, you're coming from different disciplinary, different university, and so on. This induction school, the program concerns general talks on ceramics and 3D printing method. And we had also the opportunity to have a talk from Richard Todd from the Journal of the European Ceramic Society, who presents you the way to write a good paper, if you remember. And also, this school was not for all of you, of pity, but all who were already engaged at that date. That was the opportunity to gather to everybody that you can constitute this network between ESR. Then after the induction school, we have organized different summer school and workshop. And we ask you to complete the individual career development plans. And then for your thesis, you had the opportunity to spend a few months in other laboratories in academic or in industrial. So here you have the list of the different schools with the dates. 3 of the summer school were organized at the same time and place as the YCAM conference. organized by the YCN of the European Ceramic Society. And then a first part of the school was devoted only to the ESR and included some lecture and practical lesson on communication, for instance, and also to have exchange between you on your research results. And the second part was lecture from specialists on the topics and was open to any young researcher. And I think that allowed for you to have a larger network outside of the program. And the third part was the conference of YCAM, and you had the opportunity to present your work to a larger community. Wow. Je sais pas, I don't know. Okay. Then I explained also there was also some specific WebEx meeting, mainly during the COVID period. We asked to you which topic you wanted to have some presentation. Here we have the list of the different topics. Some of them was suggested by the ESR. And yes, and you have also the responsible of the organization of this WebEx meeting. And the last event was the workshop on ESR certification and qualification organized by video conference or in presential on last 8th November in Barcelona. There were 29 attendees, including you, but also other young researchers who joined the event. And there was two main talk and training, additive manufacturing design standard and qualification by Eugene P. from Brunel University in UK, and a workshop group activities on certification qualification by Andreas Riel. Thus, the most interesting result achieved, what I completed by today by listen you. Today, most of you have defended your PhD thesis, and most of you have a postdoctorate or engineer position somewhere in SME or in a bigger company. Two ESR are finishing their project and will present it their thesis next year. I noted that more than 60 papers have been published in a very good international journal. And I add also something I forgot that if you remember, during the first school in Maubeuge, you have realized movies on additive manufacturing of ceramics. Many presentations of the DOC-3D printing project result have been done during the project and are planned in the future also in Europe and outside Europe. And what is very important for you, I think that you succeed to create your own network. You have joined the European Young Ceramics Network because after attendance the various YCAM conference, and I noted today also that some of you you are also member of other network in ceramics. So I thank you all for excellent work done, the good time we spent together, and also for your future project. And then I'm open to any further comment because I'm sure you did so many things that probably I forget some things. If you have other things to add, don't hesitate to say me or to send me a mail about that.
Thank you, Anne, for this nice presentation. I was not expecting so much article, in fact, but yeah. In fact, the main goal was to publish 2 articles per PhD student, but in fact, the average value is 40.2.
Yes.
It's 4.2. It's 2 times more at least. And this is great. but it's very expensive because we need to do that in an open gold standard. But it's very nice because it's mean we have a lot of result also, and I would like to thank all of the people for that because it's a lot of works to work article, and you know that, and yes, it's very nice for the community also, and I think it will help people a lot. I hope. But if the students have any comment about the training on how to increase the quality of the training, some idea, or if you can also highlight a few parts which are very nice and some parts which are not nice, it's a good time also to do that.
I think if I can start, I really like when we open these schools and trainings to the public, to other students, because it allows us, like Anne said, to grow our own network with all these students, and we can also like provide them I don't know, credits or certificates. So it's very nice. I think it gave a very good image of the project. Also, maybe for the future projects, it could be nice to have more practical exercises like we had for the last school during these schools. So it can be very long, only presentation. So I think more practical exercises and practice can be nice also. And thank you again, everyone.
Thank you for your nice comment. I don't know if someone wants to add some things more or about that.
I may add that actually there were also some training that were a bit of involuntary, like implicit, like all the, I'm referring especially to all the networking that came not only between each other and between the member of the project, but also thanks to these open workshop and open schools that Nico was mentioning. We at the end we had the opportunity of expand our network and keeping it despite and also maybe thanks to the COVID period and the COVID experience, because of it like sort of I don't know, made a common thing that bond a little bit all of as a PhD in the same COVID condition. So if we can take something positive of that, is maybe this.
Yeah. Thank you for this next comment. I think it's interesting. I don't know if someone wants to do something, or maybe I don't know about the time. If we need to, I think it's time to shift. Sorry about that, but it's time for Guillaume to give a speech. I would like also to thank Guillaume, because Guillaume has spent all the day with us to hear something about scientific, but he's not a scientific guy, in fact. But I think he learned a lot about additive manufacturing and ceramics. So.
He's an expert now.
Yeah, I know.
Can give him an honorary PhD, you know?
Yeah, why not?
So thank you, everybody. So I will present the work package 7 about management and dissemination. So just a reminder of the objective of this work package. It is about project management, so about the legal aspect of and also financial, administrative issues and technical coordination, because as it was presented at the beginning of the event this morning, the project is gathering 14 different organization with 14 different PhD students at the beginning. So it was a lot of coordination for the project to run smoothly. Also, one of the very important objective was the recruitment of the ESRs at the beginning, because without ESR in the project, we couldn't have done anything. And also to coordinate the public engagement activities and dissemination and exploitation activities. Because if we are doing a project like this one, but without communicating or disseminating the result to the wider community and to the public, it is not very useful. So I just put a list of deliverables here. So that there were a lot of deliverables about the website, also about the recruitment, the consortium agreement. But yeah, I won't read all the list and the milestone, but yeah, recruitment as well for different events that we've done in the project. So I will just talk about a few points in project management. So from the beginning, we had to, with all the beneficiaries, to agree on a consortium agreement to make sure that intellectual property rights were well managed between everybody, so that collaboration between the different beneficiaries could be done without any problem. And that, for example, for private companies involved in the project, that they were not afraid of communicating, for example, confidential information that they knew that confidentiality was managed accordingly to the consortium agreement. And also, we had to make some amendment to the consortium agreement. You may recall that at the beginning of the project, it was not the DOC-3D-Printing, but DOC-3D-Serum project. And we had to change the name from at the very beginning of the project because of the 3D-Serum company in France. They thought that with the project calling itself the DOC-3D-Serum, there might be some confusion for the customers. So we decided to change the name and to call the project DOC-3D-Printing. And the other amendment also is a consequence of the COVID to request an extension of the duration of the project for 9 months more to allow some ESR to finish their research work because of some interruption during the COVID period. Also, in terms of project management, yeah, we had to do with the European Commission the amendment request and all the relation with the research executive agency and the project officer Joanna Pepa to request the amendment to explain why we wanted the amendment to the grant agreement to organize the submission of deliverables so that the European Commission could see the progress of the project and to organize the midterm meeting with the Joanna Pepa, the project officer. And so all that was done by INPT with the input of every work package leaders and every ESR, of course. And so we organized all the meetings, the kickoff meeting in Toulouse at the very beginning of the project. Then with Anne and also all the beneficiary organizing the schools. That was, yeah, it was a bit sad not to be able to meet physically for all the schools, but yeah, at least we met virtually. And also all the supervisory board meetings all along the course of the project. So we had about 2 meetings each year so that we could talk about potential issues that we were facing and to talk about the progress of the project and the plan for the next months and organizing all the projects. So just talking about the recruitment of ESR, so we decided to have a centralized process organized by the coordinator. So from the job description template to the guidelines for the interview, also through the publication of vacancies. So we provided some templates so that it was quite a homogeneous process And when candidates wanted to apply, it was the same process to apply for all the beneficiaries. And the feedback we had afterwards was that the process was quite easy for the candidates, which was the objective. So that's a good point. We received about 140 applications from 33 different nationalities. Just put some figures about the proportion of male and female applicants, which basically are more or less the same as the ESR that were recruited finally. And all the 14 ESRs were recruited in May 2019. And about dissemination and exploitation activities. So the main communication channels were the website created specifically for the project, the Twitter account and the LinkedIn account, which was also used by the ESR to publish the news of the project. And for example, also they were able to share when a paper was published, for example, or where the PhD defense of one of the other ESR was done. And also a YouTube channel that was used to share, for example, the presentation video that Anne mentioned before that was made during the summer school in Maubeuge. But also in the YouTube channel, you can find the PhD defense of some ESR when the PhD defense was recorded. Also, we created some communication materials. So, for example, in the picture from the video, you can see that ESR were wearing some T-shirts with the project logo. We had some business card and the video. And there were, as all the ESR mentioned, participation to many events, many conferences, and also not only participation to events, but also taking part on the organization of different events. So the YCAM forum, but also some of the ESR participated to the Marie Curie General Assembly, and they proposed to organize the next one in Toulouse. So because of COVID, that could not be done, but that was also very important at that time. And it was mentioned, a lot of publication. As David said, we were not expecting that many publication, but that's a sign that the project was quite successful in terms of scientific outputs. So I just put some pictures. So this picture is from the kickoff meeting back in May 2018 in Toulouse. So with all the beneficiaries gathering together in Toulouse. So which was quite nice, and we can see the old logo and the old name of the project, DOC-3D-Printing. This one from Birmingham, the first induction school when ESR met together for the first time in Birmingham. And then with the T-shirt with the logo in Maubeuge, the second time where we all met together, which was a good time as well. And then, because of COVID, we organized some video meetings. So I believe that this is a WebEx meeting with the scientific presentation with all the people from the project. But there were also a lot of poster presentations, some ESR meeting during conferences. So I believe in Portugal, in Shaping 7. And I believe that some of you may recall that the using Gather Town to organize the YCAM event because we couldn't meet physically. There were some virtual conference, which was quite nice. And then the Zoom meeting for summer school and Easter school. So that's a pity that we are not able to meet all together with COVID, but we had some opportunity to meet as well. So that's it for Work Package 7. I have just one slide for the Work Package 8, which was a Work Package about ethic requirements. So basically, the objective was to ensure the compliance with the ethics requirements, and basically about the relevant local national guidelines or legislations. So we had to make sure that in the project, we complied with all the regulations. So basically, we did a report on that with a risk assessment that was made by each beneficiary for the ESR they have recruited. And in the risk assessment, control measures and safety procedures were indicated for all the risk identified. So that was just this report, and make sure that in the project we were complying with all the legislation and regulations. So that's it, and I believe that it's just time to congratulate all of you for the awesome achievement that you performed in this project.
But thank you, Guillaume, for this nice presentation, and thank you all of you for that. And maybe I would like to thank especially Guillaume, because he did a very great job. It was very easy for me to coordinate. I think he helped a lot of people in this consortium. And I don't know how much to thank Guillaume for that. It was very, very easy. And it's a very important point, because we have a lot of administrative in European project. And I think with other people, it would be not so easy to do this kind of things. But thank you again for that.
Yes, David, I would like also, yes, to personally ask Guillaume, because he continued to help us with another ETN project. And then we know that the role of Guillaume was very important when we compare with the help that we have in the other project. I will not say the name. Donc we know that it's very, very important, the role of Guillaume, and it's a big part of the, how to say, réussite of the, all this is okay now. Donc thank you, and I think everybody, we can applaud you.
Yeah. Sure. And the project is not really finished. In fact, it's a final meeting, but the project will finish the 31 of January. And after that, we need to do many administrative works. I think the deadline, we need to submit 2 or 3 months.
Yeah, 2 months after the end of the project, we'll have to submit the final report. So yeah, together all the report and the accomplishment of the project.
It means we need to do some update of article or many things before the end of the project, and you will receive some email from us. Sorry about that, but we need this information a lot. And yes, again, I would like to thank all these people. It was very funny for me, because I'm thinking about when I start to write this project. I think it was in Birmingham. I was with GOCAM, the same place.
Yeah.
In fact, in a university, in a small house.
Yes,
it was very, very funny. And we say, oh, we can maybe try to do some project. And
almost 10 years ago.
9. I think it started 8 years ago.
14, yeah. We were together.
It's a little bit crazy, because we need time to go to the end of this project. But yes, it's funny because when I write some things between eating something, I think, oh, it could be nice. We need to check, but sometimes it. Today, I think I choose to put it in public. I think when I take some coffee, I think I remember that, but sorry about that. Maybe it could be private or public, but with my tea, I choose public one. Sorry. But it's nice for other people. I don't know if you want to add more comment or more things about the project, but if you want to, you can do it now. As you wish. Maybe Aaron, as a representative of OSR, you have something also to say.
Yeah, actually, I was gonna say very similar things like my other friends, but I think we can thank you for everything, for creating this project. And when you said you start writing this project or even having an idea 8 years ago, it's actually something very new. Like even right now, we are sometimes having problems to find data or ideas about additive manufacturing of ceramics. But thinking about this 8 years ago was a great move. Thank you so much for creating this opportunity for us and for putting this trust in us, because we were selected, and you, Guillaume, like all other beneficiaries, you were always there when we needed. And it was very easy to communicate with you. And I think all of us had like great opportunities and days with you. Thank you so much for this opportunity, really.
Okay, but we need to keep in touch, and I hope maybe in 5 years, 10 years, we can try to organize something just to see what's happened.
Yeah.
But thank you.
Yes, and there is the meeting in Lyon in July in ceramics. If you
yes, in
you want to
we...
attend, and there is a conference, a seminar, a conference, a symposium on modeling. We talk modelization. There's donc it's 2 to 6 July in Lyon.
Yes, and maybe a specific session for
there is modeling. Yes.
I think they will speak about additive manufacturing because now it's everywhere.
Yes.
And what else? I think maybe one specific session about people which perform the PhD in France also.
I think that there will not be a special session, but we will organize something to gather them together and probably a lunch together. Yes, but not talk, because it's difficult to. The topics will be so different. It's different to group in the same symposium, and to ask to present in different symposium. The objective is to meet them together, or probably a lunch or something like that. But this, if you know people who presented a thesis in France and go back to their country or another country, you can send us the information. We are collecting that.
Yeah.
I just want to say that for my colleagues, the ESR that are in the academics, that I'm waiting for the second generation of DOC-3D-Printing European project or sort of like. So contact me and I will be the industrial partner of your
yes,
of your
sure.
leading European project. Sure. We can
And,
do it.
yes, I think we can try to do these kind of things for sure. And just we will put this movie online. We will probably perform a few cuts because we have some technical issues sometimes. And also, and maybe I will ask to each partner or beneficiary to do a short movie or video just to introduce, but just a few words, because it could help also to have this, and we will put that in the YouTube channel of this project. And just I think it would be interesting for people which are not members of the project to know a little bit as a partner involved, and to have a link with that. And what else? I think we are close to the end.
Yeah.
I don't know.
Yes, David. And in Lyon, before the conference, a school will be organized on microscopy characterization of ceramics. All the new technique in microscopy. Those
Interesting.
you can attend also, because it's for young ceramists. But I will send you the information to all of you.
Okay. Okay. Thank you for that. Maybe it's time to conclude. But if you have something to say, it's now. Or never. No. Or by email after. Don't worry. Just maybe Guillaume might need to have a permanent email in case of we need to contact you, because maybe you will change your email from one institution to another.
I believe that also for the European Commission, they are performing kind of survey like 2 or 3 years after the ESR have finished their contract to know where they moved to. So I believe that the email address should be recorded in the European platform. So if you have like a permanent email address that we can put on the platform, or just to make sure that the email that is on the platform is a permanent one, that will be good.
Okay.
Okay.
Thank you again, and I wish you a pleasant day, holidays, or so maybe Christmas or whatever you want, on Happy New Year's, in fact. And I hope to see you soon for many other conferences. Thank you again.
Okay,
Thank you very much again.
Bye bye.
Bye.
Bye. Thank you.
Happy
Bye.
holidays, all of you.
Bye.
Christmas.
See you soon, everyone.
Merry.
See you.
See you.